is that science is more than a body of knowledge. It's a way of thinking, a way of skeptically interrogating the universe with a fine understanding of human fallibility.
What if everything you thought you knew about Earth's past was a meticulously crafted illusion? For eons, we've believed humanity is the pinnacle of intelligence, the first architects of civilization. But what if that's a carefully curated lie? Imagine a forgotten history, buried beneath miles of rock and aeons of time, where another advanced species rose, built, thrived, and vanished, leaving behind only whispers and anomalies that modern science struggles to explain. This isn't just a thought experiment, it's a journey into the geological record, an examination of unexplained phenomena, and a radical re-evaluation of what it means to be first. Prepare to question everything, because the evidence, if we dare to look, might just be hidden in plain sight. There is a simple question that almost never appears in textbooks or documentaries about human origins. It is not because the question is silly or unscientific. It is because once you ask it seriously, everything that follows becomes unstable. What if we are not the first intelligent species on Earth? Not the first humans, not the first tool users, not the first creatures capable of complex thought, planning, technology, or even civilization? What if intelligence did not begin with us, but with something far older that rose, changed the planet, and then vanished long before history began? This question sounds outrageous only because of how we were taught to think about time. Human history feels long to us. 10,000 years seems vast. 100,000 years feels unimaginable. But Earth is not thousands of years old. It is more than 4 billion years old. In that span, all of recorded human civilization occupies less than a thin scratch on the surface of time. When viewed from that perspective, the idea that intelligence might have emerged more than once does not sound impossible. It sounds statistically reasonable. Yet the moment this question is raised, it is often shut down. We are told that there is no evidence. We are told that if such a civilization had existed, we would have found clear traces of it by now. We are told that science has looked and found nothing. But this confidence rests on an assumption that rarely gets examined. The assumption that evidence always survives. The assumption that the geological record is complete. The assumption that intelligence leaves permanent marks that cannot be erased. What if those assumptions are wrong? What if the absence of obvious ruins does not mean nothing existed, but instead means we misunderstand how fragile evidence really is over deep time? This is where the question becomes uncomfortable, because if it is possible that evidence can be erased, recycled, buried, or misinterpreted, then certainty collapses, and with it collapses the comforting idea that we know where intelligence began. The history we are taught is linear, simple. Life begins. It evolves slowly. Intelligence appears once, civilization rises once. Everything before us is primitive, everything after us is progress. It is a story that places modern humans at the peak of a long and inevitable journey. But linear stories are appealing precisely because they remove doubt. They turn complexity into inevitability. They make our existence feel special, protected, and final. Earth does not behave that way. Earth resets itself. Continents move. Oceans disappear and return. Entire ecosystems rise and fall. Species that dominated the planet for tens of millions of years vanish so completely that only a handful of fossils remain. Most leave nothing at all. Over 99% of all species that have ever lived are extinct. Most of them left no recognizable trace. Their bones dissolved. Their habitats were crushed, melted, or subducted into the mantle. Their stories ended without witnesses. Why would intelligence be exempt from this process? This is not a question of belief. It is a question of probability. If life arose relatively quickly on Earth, which it did, and if intelligence is an adaptive strategy rather than a miracle, then it becomes difficult to argue that it could only happen once in 4 billion years. Yet, we treat the idea as taboo. We rarely ask whether our definition of intelligence is too narrow. We assume it must look like us, think like us, build like us, use the same materials, leave behind cities and monuments that last forever. But even our own cities will not last forever. If humanity disappeared tomorrow, the world would erase us faster than we like to imagine. Within a few hundred years, most buildings would collapse. Within a few thousand, forests would reclaim roads and concrete would fracture into dust. Within a 100,000 years, almost everything we built would be unrecognizable. Given 1 million years, even our largest cities would be reduced to thin chemical traces in sediment. After 10 million years, the planet would look untouched. This is not speculation. It is geology. So when we say we would know if someone came before us, what we are really saying is that we believe evidence is permanent, but nothing on Earth is permanent. Not stone, not metal, not even mountains. This is where the question shifts from provocative to serious. If evidence can be erased, then the lack of evidence is no longer proof of absence. It becomes a gap, and gaps are not conclusions. They are invitations to investigate. The problem is that this investigation leads into uncomfortable territory, because once you admit that intelligence could have existed and vanished, you must confront the possibility that some of the anomalies we have already found might not be mistakes or coincidences. You must ask why certain discoveries are explained away quickly, why some data is classified, why some objects disappear into archives and are never discussed again, why questions about deep-time intelligence are treated as distractions rather than legitimate lines of inquiry. This is not about accusing science of deception. It is about recognizing how paradigms work. Scientific frameworks determine which questions are considered reasonable. When a question threatens the foundation of a framework, it is often dismissed before it can be tested. The idea that we are not the first intelligent species challenges human exceptionalism. It challenges evolutionary simplicity. It challenges the narrative that intelligence inevitably leads to us and stops with us. And perhaps most dangerously, it challenges the assumption that progress is permanent. Because if others came before us and failed, then intelligence does not guarantee survival. Technology does not guarantee wisdom. And civilization does not guarantee continuity. That realization forces a mirror onto our own moment in history. We live in an age of immense technological power. We manipulate atoms, we alter genomes, we reshape ecosystems, we change the chemistry of the atmosphere itself. If intelligence has appeared before and vanished, then we are not pioneers. We are participants in a pattern, and patterns are only invisible when we refuse to look for them. This series begins with a question, not an answer. The question is not whether we can prove that another intelligent species existed before us. The question is whether we can honestly claim that it did not. Once that certainty is gone, everything changes. Because the Earth is old, time is vast, evidence is fragile, and the stories we tell about ourselves may be far less complete than we were taught to believe. This is the question we were never supposed to ask. And now that it has been asked, we must follow it wherever it leads. The most common objection to the idea of an ancient intelligent species is simple and confident. If something like that had existed, we would have found clear evidence by now. This belief feels intuitive, cities feel permanent, stone feels eternal, technology feels durable. We imagine that once something is built, it leaves a mark forever. Geology tells a very different story. On Earth, nothing is built to last. Not continents, not oceans, not mountains. Everything is temporary when measured against deep time. Consider our own civilization. Right now, we cover the planet with concrete, steel, glass, and plastic. Our cities are visible from space. Our infrastructure spans continents. It feels impossible that this could ever disappear. But remove humans from the equation, and the clock starts ticking immediately. Within decades, buildings begin to decay. Metal rusts, roofs collapse, roads crack, vegetation returns. In a few centuries, most cities would be unrecognizable ruins. In a few thousand years, forests would erase almost every trace of urban life. In 10,000 years, concrete would fracture into dust and soil. After 100,000 years, even the largest cities would leave only faint chemical signatures. After 1 million years, almost nothing recognizable would remain. After 10 million years, the planet would look as though we were never here at all. This is not speculation. These are well understood processes. Erosion, weathering, biological activity, and tectonic movement are relentless. Now expand that timescale. The ocean floor is recycled roughly every 200 million years. Entire continents are dragged into the mantle and melted. Sedimentary layers are folded, crushed, and transformed by heat and pressure. What survives is not what existed, but what happened to be preserved under ideal conditions. Most of Earth's surface has been reset multiple times. This is why the fossil record is so sparse. Only a tiny fraction of organisms ever fossilize. Only a fraction of those fossils survive erosion. Only a fraction of those are ever discovered. We reconstruct entire worlds from fragments because that is all that remains. Civilizations would fare worse. Cities are not buried gently. They are eroded, scattered and chemically altered. Tools corrode, structures collapse, artifacts dissolve. Over millions of years, the difference between a city and a natural formation disappears. Even stone does not endure the way we imagine. Limestone dissolves in acidic water, granite fractures under thermal stress, basalt erodes. Given enough time, mountains become sediment. This means that if an intelligent species existed tens or hundreds of millions of years ago, the likelihood of finding its cities today is extremely low. But what about durable materials? What about metal? Metals oxidize. Iron rusts and returns to ore. Aluminum reacts and disperses. Copper corrodes. Gold survives longer, but only as isolated fragments. Metal objects do not last forever. They cycle back into the earth. What about technology, machines, infrastructure? The more complex a system is, the more fragile it becomes over time. Power grids fail, reactors decay, knowledge vanishes when populations collapse. Without continuous maintenance, technology destroys itself. Civilizations are not just physical systems, they're informational systems. When communication breaks, skills are lost, techniques disappear, written records decay, memory fades. History itself is fragile. We know this from our own past. Entire cultures have vanished within a few centuries. Languages have gone extinct. Knowledge has been lost and rediscovered multiple times, even within recorded history. Now imagine this process stretched across millions of years. The silence of deep time is not evidence that nothing happened. It is the expected outcome of everything that happened being erased. This realization reframes the question completely. We are not asking why we have not found ancient civilizations. We are asking why we expect to. The Earth is not an archive. It is a grinder. It destroys information as efficiently as it creates it. Only under rare circumstances does something survive. An object trapped in sediment, a chemical anomaly locked in stone, an isotope ratio preserved by chance. These are not monuments, they are whispers, and whispers are easy to dismiss. Once you understand how aggressively the planet erases its own past, the question changes. It is no longer why there is so little evidence of ancient intelligence. It is why there is any at all. If intelligence emerged before us, its traces would not be obvious. They would be scattered, incomplete, and easily misinterpreted. They would look like anomalies rather than proof, which means that the few anomalies we have found may not be coincidences. They may be exactly what we should expect, and if that is true, then the problem is not the absence of evidence. The problem is that we have been looking for the wrong kind. The idea that technologically advanced civilization could have existed on Earth before humans was long treated as a fringe distraction, belonging to speculation rather than serious science. Serious researchers did not ask such questions because the answers were assumed to be obvious. Then, in 2018, something unusual happened. Two scientists published a paper that did not claim ancient civilizations existed, but asked a far more dangerous question. Would we even be able to tell if they had? This paper became known as the Silurian Hypothesis. It was written by Gavin Schmidt, the director of NASA's Goddard Institute for Space Studies, and Adam Frank, a professor of astrophysics at the University of Rochester. These were not fringe thinkers, but mainstream scientists working at the highest levels of their fields. Their question was simple and unsettling. If an industrial civilization had existed on Earth millions of years ago, would the geological record preserve clear evidence of it? Most people assume the answer is yes. We imagine ruins, cities, machines, monuments, something obvious, something undeniable. Schmidt and Frank challenged that assumption. They began by examining the nature of the geological record itself. Rocks do not record everything. They record fragments. Sediments are eroded. Tectonic plates are subducted. Oceans are recycled. Heat and pressure erase detail. What survives is not a complete archive, but a distorted and incomplete one. Geologists estimate that we have access to far less than 1% of all sedimentary rock that has ever existed on Earth. The rest has been destroyed or transformed beyond recognition. That means 99% of Earth's history is missing. Against that backdrop, Schmidt and Frank asked what kinds of traces an industrial civilization might actually leave behind over deep time. Not buildings, not roads, not artifacts. Those would vanish quickly. Instead, they focused on chemical and isotopic signatures. Our own civilization is altering the planet in measurable ways. We burn fossil fuels, releasing ancient carbon into the atmosphere. We change nitrogen cycles through fertilizer production. We spread synthetic compounds across land and sea. We create radioactive isotopes through nuclear activity. These changes leave signals, but even these signals are not permanent. Plutonium does not last long on geological timescales. After a few 100,000 years, it decays into lead. Most synthetic chemicals break down and plastics fragment. Even dramatic climate shifts eventually blend into background noise. Schmidt and Frank concluded that after tens of millions of years, almost all direct evidence of an industrial civilization would be ambiguous at best. Future scientists might notice strange chemical spikes. They might see anomalies, but they would not be able to say with certainty what caused them. In other words, absence of clear evidence would not mean absence of civilization. It would mean the evidence had faded. This conclusion did not prove that ancient civilizations existed, but it destroyed the confidence that they could not have existed. That distinction matters. Science is often portrayed as a collection of facts. In reality, it is a framework of assumptions built on available evidence. When evidence is incomplete, assumptions fill the gaps. The Silurian Hypothesis exposed just how large those gaps really are. It also revealed something else. The reason the question of ancient intelligence feels forbidden is not because it violates evidence, it is because it violates expectation. We expect intelligence to be rare. We expect it to look like us. We expect it to progress steadily toward modernity. We expect ourselves to be the end point. The Silurian Hypothesis removes that comfort. It suggests that intelligence could be a transient phenomenon, a brief flare in deep time, appearing, altering the planet, then disappearing so thoroughly that even its own footprints are misread. After the paper was published, reactions were cautious. Some praised the thought experiment, others dismissed it as academic curiosity. Few followed its implications to their logical end, but the door had been opened. If science admits that it cannot rule out ancient industrial civilizations, then certainty collapses. The timeline is no longer closed. The past becomes conditional rather than fixed. This is not a failure of science. It is a moment of honesty. It acknowledges that our confidence about being first rests not on proof but on assumption. It acknowledges that deep time is hostile to memory, and it acknowledges that some of the anomalies already discovered may deserve a second look. The Silurian Hypothesis does not claim we are not the first intelligent species. It claims something more unsettling, that we do not know. And once that uncertainty is admitted, every unexplained isotope ratio, every strange object, every erased anomaly stops being an inconvenience and starts becoming a clue. Science did not close this question. It quietly opened it. And in doing so, it forced us to confront the possibility that the history of intelligence on Earth is far older, far stranger, and far less certain than we were ever taught to believe. In 1972, a discovery was made that should have rewritten everything we think we know about technology, intelligence, and deep time. Instead, it was quietly filed away as a curiosity and then largely forgotten. Deep beneath the uranium mines of Oclo in Gabon, a French scientific team led by physicist Francis Perrin noticed something strange. The uranium ore they were extracting was wrong. Specifically, it contained less uranium-235 than it should have. This mattered because uranium-235 is the isotope used in nuclear reactors and weapons. It is the part of uranium that splits easily and releases enormous amounts of energy. In nature, uranium has a very stable ratio. About 99.3% is uranium-238, about 0.7% is uranium-235. This ratio is consistent across the planet, in rocks, in oceans, in meteorites. It is one of the quiet constants of geology, except at Oclo. At Oclo, the ratio was depleted. Uranium-235 was missing in amounts that could not be explained by ordinary radioactive decay. Something had consumed it. Something had caused nuclear fission to occur. As the investigation continued, the situation became even more difficult to explain. Scientists identified not one, but 16 separate reaction zones spread across the site. These zones showed clear evidence of sustained nuclear fission. Not a brief spike, not a chaotic burst, but controlled reactions that had turned on and off repeatedly over long periods of time. The dating was unambiguous. These reactions had occurred approximately 2 billion years ago. 2 billion years. This was not a few thousand years before recorded history. It was not even a few million years before the first humans. At that time, complex life barely existed. There were no plants, no animals, no oxygen-rich atmosphere. According to everything we are taught, there was nothing on Earth capable of building or operating a nuclear reactor. Yet, a nuclear reactor had clearly operated. The scientific community, faced with this undeniable evidence, proposed a natural explanation. They theorized that under very specific and rare geological conditions, a natural nuclear reactor could form. If the uranium ore was rich enough, and if groundwater seeped in to act as a moderator, and if the conditions were just right, a chain reaction could spontaneously begin. The water would boil, stopping the reaction, and then as it cooled and returned, the reaction would restart. This on-off cycle could explain the sustained fission. The Oklo phenomenon was thus dubbed the natural nuclear reactor. While this explanation is scientifically plausible, it relies on an extraordinary confluence of rare circumstances. The uranium concentration had to be exceptionally high, the groundwater had to be pure enough to act as a moderator without poisoning the reaction, and the geological conditions had to remain stable for hundreds of thousands of years. The Oklo reactors operated for an estimated 150,000 to 850,000 years. This is a staggering amount of time for such a delicate natural balance to persist. Furthermore, the efficiency of the natural reactor was remarkable. The isotopic ratios of the fission products such as neodymium, ruthenium and samarium were consistent with what one would expect from a man-made nuclear reactor. The waste products were also contained, indicating a stable geological environment. The Oklo discovery did not prove an ancient civilization existed. It was explained away as a natural curiosity, but it did prove that nuclear fission, a process we consider the pinnacle of modern technology, could occur on Earth 2 billion years ago. It showed that the planet itself could harbour the signatures of nuclear activity, whether natural or artificial, for immense spans of time. And once that possibility is admitted, the question shifts. Are there other, less obvious nuclear signatures hidden in ancient rock layers? Perhaps not as dramatic as Oklo, but still indicative of unusual activity. Scientists analyse radiation signatures in ancient materials by looking for specific isotopes that are produced during nuclear reactions. For instance, the ratio of certain lead isotopes can indicate whether they originated from the decay of uranium that underwent fission. The presence of technetium or promethium, elements that are rare in nature but common in fission products, could also be a clue, though their short half-lives make detection over geological time extremely difficult. The Oklo phenomenon remains unique, the only known natural nuclear reactor on Earth, but its existence forces us to reconsider the definition of natural. It demonstrates that the Earth's deep past can hold secrets that directly challenge our assumptions about technological thresholds and the timeline of advanced processes. If nature can build a reactor, what else could have been built, or what other processes might have left similar, yet uninterpretable, nuclear fingerprints across the vast expanse of geological time? If cities crumble and machines vanish, something else may remain. Not structures you can touch, but changes written into the chemistry of the planet itself. Civilizations do not just build things, they alter environments. They change the balance of elements. They leave chemical fingerprints that persist long after physical objects are gone. Our own civilization is doing this right now. By burning fossil fuels, we're releasing carbon that was locked underground for hundreds of millions of years. That carbon carries a distinct isotopic signature. Living organisms prefer one form of carbon over another, and fossil fuels preserve that preference. When we burn them, the ratio of carbon isotopes in the atmosphere, oceans, and sediments shifts. Geologists already use this signal to define a new geological interval, often called the Anthropocene. It is a thin chemical layer, not a city or a monument. A future geologist would not see skyscrapers. They would see an unusual spike in carbon isotopes and ask what caused it. The unsettling part is this. When scientists examine ancient rock layers, they find similar spikes. There are moments in deep time when carbon isotope ratios shift suddenly and dramatically. The Paleocene-Eocene thermal, maximum 56 million years ago, is one example. Global temperatures rose rapidly, oceans acidified, life struggled. The standard explanation involves massive releases of methane or volcanic activity. but the chemical pattern looks strikingly similar to rapid combustion of organic material on a global scale. Another example appears at the Permian-Triassic boundary, the same interval associated with the greatest mass extinction in Earth history. The carbon shift there is one of the most extreme ever recorded. It is usually attributed to volcanic eruptions, yet the initial chemical change appears before the main phase of volcanism. These events are treated as natural catastrophes, but chemically they resemble planetary-scale disruptions of the carbon cycle, the same kind of disruption an industrial civilization would cause if it burned enormous amounts of stored carbon. Carbon is not the only element that tells this story. Nitrogen cycles are also sensitive to technological interference. Modern agriculture produces synthetic fertilizers by pulling nitrogen from the atmosphere and converting it into reactive forms. This process alters nitrogen isotope ratios across soils, rivers and oceans. Ancient sediments show sudden nitrogen anomalies at several points in Earth's history, spikes that appear too rapidly and at too large a scale to be explained easily by natural biological processes alone. These anomalies are usually attributed to changes in ocean circulation or microbial activity, but the timing and magnitude often raise questions that remain unanswered. Then there are synthetic compounds. We like to think of plastics as uniquely modern, but when researchers analysed deep ocean sediment cores, they identified long-chain hydrocarbon polymers in layers hundreds of millions of years old. The official explanation was contamination during drilling, yet the compounds appeared at depths and concentrations that made surface contamination difficult to explain. No follow-up studies were funded. Radioactive isotopes add another layer of complexity. Plutonium does not last long geologically, but uranium and thorium do. Their ratios change in predictable ways when nuclear reactions occur. These ratios are remarkably consistent across the solar system, except where they are not. The uranium anomalies at Oklo are the most dramatic example, but they may not be the only ones. Subtle variations in isotope ratios have been detected in ancient formations and are often dismissed as measurement error or natural irregularity. Individually, they mean little. Together, they form a pattern that is difficult to ignore. Chemistry has no memory of intention. It records only what happened. It does not know whether a reaction was caused by a volcano, a meteor, or a machine. It only records the final state of the elements. Therefore, these chemical anomalies, these out-of-place isotope ratios, and these unexpected compounds in deep geological layers become compelling whispers from a lost past. They are not direct evidence of ancient factories or cities, but they are exactly the kind of geological fingerprints that an industrial civilization would leave behind, even if all physical structures had vanished. The scientific attempts to explain these anomalies often rely on complex and sometimes ad hoc natural processes, sometimes stretching the bounds of probability. This does not mean those explanations are wrong, but it does highlight the fact that when faced with data that challenges existing paradigms, the tendency is to find the most naturalistic explanation, even if it is highly improbable, rather than considering a more radical alternative. Beyond the elemental cycles of carbon and nitrogen, the search for a pre-human industrial footprint must delve into the inorganic backbone of technology: metals. Nature distributes metals in predictable patterns. All bodies form through hydrothermal vents, magmatic segregation, or sedimentary precipitation. These processes leave a signature of gradual accumulation and specific mineral associations. Industrial extraction, however, does the opposite. It concentrates pure elements and scatters the waste. If a civilization existed, it would have hungered for the same conductive and resilient materials we prize: copper, gold, rare earth elements, and platinum group metals. The geological record should, in theory, show shadows of depletion. If a global society mined the accessible surface veins of copper or tin to exhaustion, a future geologist might find a puzzling absence of these ores in rock strata, dating to a specific era. Yet, proving a negative is scientifically perilous. A more positive signal would be the presence of refined alloys where they do not belong. Nature rarely creates pure aluminum. It binds it tightly in bauxite. Finding a microscopic trace of refined aluminum or titanium alloy in a 300-million-year-old sediment core would be the geochemical equivalent of finding a wristwatch in a dinosaur fossil. Over millions of years, physical artifacts corrode and dissolve, but the ions do not vanish. They migrate. They would reform into secondary minerals that should not exist in that specific geological context. halos of metallic contamination that mirror the heavy metal pollution currently settling into the river deltas of the 21st century. Consider the technosphere trace of rare earth elements, or REEs, like gadolinium, used extensively in modern electronics and medical imaging. These elements are not rare in the crust, but they do not naturally concentrate in river water. Today, however, anthropogenic gadolinium is entering the oceanic sediment cycle at rates orders of magnitude higher than background levels. Millions of years from now, this will form a distinct razor-thin chemical horizon. If we detected a similar coherent spike of lanthanum or neodymium in the Jurassic strata, a spike unaccompanied by the volcanic activity that usually generates such anomalies, we would lack a standard geological model to explain it. We would likely categorize it as a geochemical curiosity or a sampling error, largely because the alternative requires rewriting history. Furthermore, the duration of an industrial civilization poses a massive detection problem. This is the resolution issue of the geological record. The Earth is 4.5 billion years old. Our industrial phase has lasted barely 2 centuries. In the context of deep time, 200 years, or even 2,000, is invisible. It is thinner than a single grain of sand in a sedimentary layer. If a species rose to industrial prominence, burned through its resources and collapsed within a span of 5,000 years, the resulting layer in the rock record would be millimetric. It could easily be eroded away by wind or water before it ever lithified. Whole eras of Earth's history are missing due to these unconformities, vast gaps where rock was worn away rather than deposited. The Great Unconformity, a geologic feature found across the globe, represents a missing billion years of time. 1,000 civilizations could be hidden in that void, ground to dust and washed into the subduction zones where the planetary crust is recycled into magma. This recycling of the crust is the ultimate eraser. Plate tectonics ensures that the ocean floor is replaced roughly every 150 million to 200 million years. Any industrial evidence left on the deep ocean plains of the Triassic is gone, melted back into the mantle. We are left only with the continental shields, which are older but subject to the relentless scouring of wind, rain and glaciers. This forces the search for anomalies into the realm of the ultra-persistent synthetic molecule, the forever chemicals. While simple polymers might degrade per- and polyfluoroalkyl substances, PFAS possess carbon-fluorine bonds that are among the strongest in organic chemistry. They do not occur in nature. If a prior civilization developed non-stick coatings, refrigerants or fire-retardant foams, these molecules might persist in the deepest, most stagnant clay deposits. Finding a complex fluorinated organic molecule in a sample of Carboniferous coal would be inexplicable by biotic evolution. Nature builds complexity, but it tends to use specific pathways. It does not synthesize molecules that are thermodynamically expensive and metabolically useless. The presence of such a compound would imply a synthetic intent, a laboratory rather than a leaf. However, the most profound chemical anomaly might not be a molecule at all, but a biological manipulation that leaves a chemical echo. Industrial civilizations homogenize the biosphere. We transport species across oceans, creating a new Pangaea where invasive species dominate local ecosystems. This biotic mixing alters the chemical composition of the soil and the sedimentation rates of the oceans. The rapid spread of a specific nutrient-hungry plant species across the globe would alter the strontium and calcium ratios in the fossil record. If we look at the timeline of the Earth, there are moments where the biosphere seems to convulse and simplify. The recovery period after the end-Permian extinction saw the world dominated by a single genus of reptile, Lystrosaurus, which accounted for a staggering proportion of all terrestrial vertebrates. Was this just a survivor of a natural disaster, or the livestock or companion animal of a vanished age, proliferating unchecked in the ruins? We see the bones, but we rarely correlate them with the sudden anomalous spikes in soil chemistry that would accompany a planetary-scale monoculture. If Earth is too active, too prone to erasing its own memory, then the most enduring evidence might lie off-planet. The chemical anomalies of the Earth are subject to the water cycle and tectonic grinding. The Moon is not. A spacefaring industrial society, even a rudimentary one, would eventually leave the gravity well. They would leave junk. The Clark Belt, the ring of geostationary orbit, is currently filling with dead satellites. Over millions of years these objects will decay, but their constituent elements will not leave orbit easily. They will be pulverized by micrometeoroids into a ring of dust. This dust would have a telltale chemical signature, distinct ratios of aluminum, titanium, gold, and silicon that do not match the mineralogy of the Earth or the Moon. Eventually, this dust would rain down on the lunar surface. The Moon, lacking an atmosphere and tectonic activity, acts as a pristine museum shelf. Its regolith, soil, accumulates layers of cosmic dust undisturbed for billions of years. If we were to conduct a deep core chemical analysis of the lunar soil, we might find layers enriched with the corrosion products of ancient alloys. A layer of high-purity titanium oxide buried 10 meters beneath the lunar surface would be difficult to explain as a product of asteroid impacts. Impactors are mostly chondritic or metallic iron nickel. They do not carry refined alloys. The anomaly would be subtle, a few parts per billion, but to the trained eye of a spectrograph, it would scream of artificiality. Similarly, the isotopic composition of the planets themselves offers a potential archive. We assume the surface of Mars is red due to natural oxidation over eons. We assume the high ratios of xenon-129 in the Martian atmosphere are the result of natural loss processes or ancient cosmic ray spallation. However, xenon-129 is also a primary signature of nuclear fission. The values on Mars are high enough that some physicists have jokingly, and controversially, referred to them as evidence of a natural nuclear event far exceeding the scale of the Oklo reactor on Earth. While natural explanations are currently sufficient to satisfy the consensus, the data exists in a grey zone. It sits right at the edge of what natural models can accommodate. This is the recurring theme of the Silurian inquiry. The data is never impossible, just highly improbable. We must also consider the ultimate fate of our own chemical legacy to understand what to look for. Our cities will not remain as concrete skeletons. Concrete is porous. Water enters, steel rebar rusts, expands and shatters the stone. Within 10,000 years, a skyscraper is a pile of rubble. Within 1 million, it is a geological layer. But what kind of layer? It will be a stratum of unusual hardness, rich in carbonates but spiked with iron oxides and trace metals. It will form a rock type that currently has no name. Geologists of the future might call it urbanite or anthropobreccia. This layer will also contain technofossils, not just shapes, but chemically altered matrices. Plastiglomerates are already forming on Hawaiian beaches, plastic melted by campfires, fusing with sand, basalt and coral into a new, durable rock. These hybrid stones are waterproof and resistant to decay. Buried under pressure, they will flatten and fossilize. A future chemical analysis of such a rock would yield a hydrocarbon signature that looks like oil, but has the structural complexity of a polymer. If we found a flattened nodule in the Devonian shale that tested positive for the chemical bonds of bakelite or nylon, we would likely dismiss it as sample contamination from the modern plastic equipment used to drill the core. Our own ubiquity blinds us to the possibility of the past. We are so saturated in our own chemical byproducts that we cannot easily distinguish a pre-existing signal from our own noise. The final, and perhaps most disturbing chemical anomaly is the atmosphere itself. We view the current composition of the air as a baseline, fluctuating only due to volcanoes and biology. But the atmosphere is a chaotic system that can settle into different stable states. Industrial outputs, CFCs, sulfur hexafluoride and other potent greenhouse gases have lifetimes ranging from decades to millennia. However, the trigger they pull can last much longer. If a civilization triggers a runaway greenhouse effect, the chemical weathering of rocks changes. Higher temperatures and CO2 levels accelerate the breakdown of silicate rocks, which eventually draws down the CO2. This is a negative feedback loop. But the recovery leaves a scar, a massive global deposit of carbonate rocks, limestones and dolomites formed rapidly in oceanic basins. We see these massive carbonate platforms throughout the geological record. They are usually attributed to the proliferation of shell-making life, but the rate of deposition sometimes defies biological limits. A hypercarbonate event, where the ocean dumps its dissolved carbon into rock at a suicidal speed to correct the atmospheric balance, looks chemically identical to the aftermath of a massive industrial carbon injection. The Capitan Reef in the Permian, or the vast chalk deposits of the Cretaceous, are viewed as monuments to life. Seen through a different lens, they could be the tombstones of a climate system desperately trying to heal itself from a provocation that was not natural. Ultimately, chemistry has no loyalty to the narrative of human exceptionalism. It follows the laws of thermodynamics and stoichiometry. The anomalies discussed, the isotopic spikes, The impossible alloys, the synthetic polymers, the nuclear signatures are puzzle pieces scattered across a billion-year floor. The scientific method demands parsimony. We must choose the simplest explanation. A volcano did it is always simpler than a vanished civilization did it, because volcanoes are observed phenomena and ancient civilizations are not. But this logic is circular. We do not observe them because we define the evidence they would leave as natural. We are looking for a mirror in the rock, hoping to see our own face reflected in the deep past. Instead, we see only shadows and distortions. But as our own chemical footprint deepens, understanding how an industrial civilization alters the planetary chemistry becomes less of a speculative exercise and more of a survival necessity. By studying the impossible anomalies of the past, we might not just be hunting for ghosts, we might be reading the user manual for a planet that has been broken and fixed many times before. The chemicals are there, waiting in the strata, silent witnesses to the possibility that the Anthropocene is not an event, but a recurring cycle. Earth's history is punctuated by colossal events of biological upheaval, periods where the vast majority of life on the planet vanished in relatively short geological timescales. These are the mass extinctions, and there have been 5 major ones, each profoundly reshaping the course of evolution. The most famous include the Cretaceous-Paleogene extinction, which wiped out the dinosaurs, and the Permian-Triassic extinction, often called the Great Dying, which annihilated over 90% of marine species and 70% of terrestrial vertebrate species. For decades, scientists have diligently sought natural causes for these catastrophic events: massive volcanic eruptions, asteroid impacts, or drastic climate shifts. Yet, when we examine these extinctions through the lens of the Silurian Hypothesis, a different set of questions emerges. Could some of these events, or at least aspects of them, have been influenced by something other than purely natural phenomena? Consider the Permian extinction, roughly 252 million years ago. It stands out not just for its severity, but for its unique characteristics. Evidence points to rapid and extreme global warming, ocean acidification, and widespread anoxia, a lack of oxygen in the water. The leading hypothesis attributes this to the Siberian Traps eruptions, a massive volcanic event that released enormous amounts of greenhouse gases and aerosols. However, the timing and specific chemical fingerprints of the Permian extinction have always presented challenges. The carbon isotope shifts, for instance, are incredibly dramatic, suggesting a rapid release of greenhouse gases on an unprecedented scale, even for volcanism. Moreover, there is an unusual pattern of elemental enrichment in some Permian-Triassic boundary layers, including heavy metals, that is difficult to fully explain by volcanic activity alone. When comparing natural versus artificial extinction triggers, our own industrial civilization offers a stark parallel. We are currently causing rapid climate change, ocean acidification, and are on the brink of a potential 6th mass extinction. The chemical signatures of our current impact on the planet, particularly the rapid release of fossil carbon, bear a resemblance to the geological fingerprints observed in some ancient extinction events. This is not to say that an ancient civilization caused the Permian extinction, but it prompts a critical question. If an advanced, energy-intensive civilization were to collapse, could its industrial waste, its rapid alteration of atmospheric chemistry, or even its accidental or intentional release of destructive forces, trigger an extinction event that would look strikingly similar to a natural catastrophe in the deep geological record? The Permian extinction shows evidence of rapid environmental changes that are consistent with both extreme natural events and large-scale industrial activity. The massive release of greenhouse gases, the widespread anoxia, and the acidification of the oceans are all symptoms that could arise from either source. If an ancient civilization reached a technological level similar to, or even exceeding our own, its footprint on the biosphere could have been immense. The very technology that sustained it might, in its collapse or unchecked expansion, have become the trigger for global devastation. This perspective does not replace existing theories, but offers an alternative lens through which to view the evidence. It suggests that some of the unusual features of past mass extinctions, those aspects that don't quite fit neatly into purely naturalistic explanations, might be the blurred, ancient echoes of a technological society that inadvertently or deliberately pushed Earth's systems past a critical threshold. leaving behind a planetary scar that we now attribute to the blind forces of nature. To explore this disturbing possibility further, we must consider the specific mechanisms of collapse and how they would translate into the language of rocks and isotopes. If a civilization ends not with a whimper but with a bang, a suicide pact with the planetary environment, the resulting stratigraphy would differ subtly but significantly from that of a purely stochastic natural disaster. A meteor impact is a singular high-energy event that creates a distinct layer of iridium and shocked quartz, followed by a nuclear winter effect. An industrial collapse, however, is a process, a crescendo of dysfunction that might last centuries before the final silence. This distinction allows us to hypothesize about the smear versus the spike. A natural catastrophe often presents as a sharp spike in the geological record. The asteroid that ended the Cretaceous period struck in a moment. The sediment layer marking the boundary is razor thin. In contrast, the collapse of a global industrial system would likely resemble a smear, a chaotic fluctuation of climate indicators, oscillating violently before flatlining. We might see a rapid spike in carbon dioxide, followed by a desperate artificial attempt to cool the planet. Perhaps a sudden injection of sulfur aerosols, geoengineering, appearing in ice cores or sediments, resulting in a volcanic winter signature without the accompanying basaltic lava flows. This would be followed by a rebound warming, as the cooling technology fails but the greenhouse gases remained. Such a whipsaw climate signal, where the Earth swings wildly between hot and cold extremes within a few thousand years, is difficult to explain through natural feedback loops, which tend to be slower and more rhythmic. Yet, looking at the high-resolution data of the end-Permian extinction, we see puzzling instabilities in the climate leading up to the main event. These precursory tremors are usually attributed to early phases of volcanism, but they could equally represent a civilization fighting a losing war against its own thermodynamic exhaust. Furthermore, we must look at the specific lethality of these extinction events. The Great Dying killed insects. This is a profound anomaly. Insects are the great survivors of biological history. They are resilient to radiation, famine, and climatic shifts. The Permian extinction is the only known mass extinction of insects. What kills insects specifically? In our modern context, the answer is insecticides and synthetic chemical agents. If an ancient biosphere were saturated with a persistent nerve-attacking agent, perhaps a weapon of war or a runaway agricultural control measure, it would leave a biological vacuum that natural climate change alone cannot explain. We would see a selective disappearance of specific arthropod lineages, while other, perhaps more fragile marine life held on slightly longer. This selective extinction pattern, a sniper's shot rather than a shotgun blast, is a hallmark of technological interference. Then there is the issue of the coal gap. Following the Permian extinction, there is a period of millions of years in the early Triassic where coal simply stops forming worldwide. The standard geological explanation is that the plants which formed coal went extinct, or that the fungi which decompose wood became hyperactive, the fungal spike. However, an alternative darker hypothesis exists. What if the coal is missing because it was harvested? If a civilization existed at the cusp of the Permian, the massive coal forests of the Carboniferous period would have been their primary fuel source. A global civilization would strip mine the accessible surface deposits, leaving only the deep, inaccessible seams for future geologists to find. When we look at the geological record, we see a massive hiatus in coal deposition. If this hiatus was natural, it implies a total collapse of the terrestrial flora. If it was artificial, it implies resource exhaustion. The fungal spike, a layer of fungal spores found globally at the boundary, is interpreted as fungi feasting on the dying forests, but it could also represent the decay of vast biological waste dumps or the breakdown of wooden infrastructure on a planetary scale. The sudden conversion of the world's biomass into dead organic matter is consistent with a biosphere that has been poisoned or defoliated, reminiscent of the aftermath of wide-scale chemical warfare. We must also consider the legacy of nuclear technology. While uranium and plutonium isotopes from a reactor or a bomb decay relatively quickly, in geological terms, the daughter products and the physical alteration of the environment do not. A global nuclear exchange would leave a specific layer of glass microspherules, sand fused by heat exceeding that of volcanoes, but differing in distribution from asteroid impacts. Impact glass is distributed radially from a crater. War glass, would be clustered around the centres of population and industry, specifically on continental shelves and river deltas. Because of plate tectonics, most of these potential city sites from 250 million years ago have been subducted into the Earth's mantle. However, the isotopic echo would remain in the atmosphere and ocean. The sudden release of huge quantities of xenon-129, a byproduct of nuclear fission, would eventually settle into the sediment. While natural reactors, like the Oklo phenomenon, exist, they are localized. A global layer of fission byproducts would imply a global release event. When we analyze the isotopic composition of ancient atmospheres trapped in fluid inclusions within crystals, we are looking for these subtle deviations from the solar system's background average. Another avenue of inquiry involves the presence of exotic minerals. An advanced civilization would likely synthesize materials that require extreme pressures, temperatures, or chemical conditions not found in nature. Consider the forever chemicals and advanced ceramics. But consider also the concentration of rare elements. We mine gold, platinum, and rare earth elements, concentrating them from dispersed ores into pure ingots. If a civilization collapses, these hordes of purified elements do not disappear, they scatter. A future geologist might find a placer deposit in a 200 million year old riverbed that contains a statistically impossible concentration of pure gold or platinum nuggets, lacking the natural alloy mixtures found in raw ore. This is the concept of geochemical halos. Nature distributes elements based on their chemical affinity. Gold likes to hang out with quartz and sulfides. It does not naturally congregate with refined aluminum or titanium. Finding a microscopic grain where titanium and gold are fused together in an unnatural alloy within a Permian sediment would be the smoking gun. We often dismiss such findings as micrometeorites, which can contain exotic alloys. But meteorites have distinct extraterrestrial isotopic signatures. An industrial meteorite, a piece of a rusted ancient machine, would have Earth-like isotopic ratios but an alien structural composition. The most chilling aspect of the Silurian hypothesis in the context of mass extinctions is the potential for biological warfare to look like a plague. Evolution is an arms race, but it is a slow one. A predator evolves a better tooth, the prey evolves a thicker hide. This takes millennia. In the fossil record, we sometimes see species vanish instantly, replaced by nothing. This suggests a pathogen so virulent and fast-acting that evolution had no time to respond. While natural pandemics occur, they rarely wipe out entire families of diverse species across the globe simultaneously. A synthetic pathogen, however, engineered for maximum lethality or jumping species barriers via gain-of-function tinkering, could cause a biotic crash that mimics a sudden environmental collapse. The end Permian event saw the loss of over 90% of marine species. The speed of this collapse is still debated, but if it happened within a few decades or centuries rather than millennia, it defies most natural models of ocean chemistry change. It demands a catalyst. Moreover, if we view the Earth as a closed system, an industrial civilization acts as our entropy accelerator. We take low-entropy resources, fossil fuels, ores, and convert them into high-entropy waste, heat, CO2, mixed landfills. A mass extinction event is, thermodynamically, a massive spike in planetary entropy. The biological order breaks down into chaos. Detecting the rate of the entropy increase is key. Natural disasters are high-entropy events, but the build-up to them is usually distinct. A volcano builds pressure. An asteroid has a trajectory. An industrial civilization, however, exhibits exponential growth. The chemical signatures it leaves would show an exponential curve, a hockey stick graph, immediately preceding the crash. When we look at the isotopic data for the Paleocene-Eocene thermal maximum, PETM, or the Permian-Triassic boundary, we are essentially curve-fitting. We have a few data points separated by thousands of years. We connect the dots with a smooth line and call it a natural trend. But if we had higher resolution, if we could see the year-by-year changes, we might see the jagged, frantic signature of a market economy consuming the world. We might see the Monday morning spikes in pollution, the seasonal shifts of industrial agriculture, the sudden dips corresponding to pandemics or wars, all compressed into a single, chaotic sediment layer. The absence of macrofossils, skyscrapers, machines, bones, is expected. The Earth is a rock tumbler. It grinds mountains to sand, but the chemical ghost remains. The ultimate implication of this perspective is that the great filter of the Fermi paradox might not be in the stars, but beneath our feet. We ask why the universe is silent. Perhaps the silence is the norm because advanced civilizations are self-limiting reactions. They are not stable states of matter, they are flash fires. They burn the stored carbon, poison the water, reset the thermostat, and then extinguish themselves, leaving the biosphere to slowly recover over 10 million years. If the Permian extinction was indeed such an event, then the rise of the dinosaurs was not just a new chapter, but a recovery from a failed experiment. The dinosaurs dominated for 160 million years, far longer than we have existed, perhaps because they fit into the ecological balance rather than trying to override it. They did not industrialize. They did not dig up the carbon of the Carboniferous. In this light, the study of mass extinctions becomes a study of existential risk. We are analysing the crime scenes of the past to solve the potential murder of the future. The anomalies, the uranium spikes, the vanishing insects, the impossible warming curves, are warnings written in the only language that lasts, stone. They suggest that the threshold for planetary destabilization is lower than we think, and that we are walking the same path that may have been walked before. The Earth does not care if the CO2 comes from a Siberian volcano or a smokestack. The feedback loops are the same, and if the machine stops, the silence that follows is absolute. The challenge for modern science is to stop forcing the data to fit a gradualist natural narrative and to have the courage to ask if the catastrophes of the past were actually failures of a different kind. Earth is not merely old, it is constantly renewing itself, often violently. This relentless geological activity acts as a planetary reset button, systematically destroying and transforming its own historical record. Plate tectonics, for instance, ensures that no part of the ocean floor is older than about 200 million years. Entire swaths of oceanic crust are continuously formed at mid-ocean ridges and then subducted back into the Earth's mantle at trenches, taking with them any sediments, artifacts, or chemical signatures that might have accumulated. This means that if an ancient civilization thrived on a continent that has since been subducted, or if its cities were built on land masses that have been eroded into the sea and then recycled, virtually all direct evidence would be utterly erased. Even continental crust, while more stable, is subject to immense forces. Mountains are uplifted and then weathered away. Sedimentary basins are filled and then compressed, heated and metamorphosed, turning ancient layers into unrecognizable rock. The concept of cyclical civilizations fits neatly within this framework. If intelligence is a recurring phenomenon, arising multiple times over Earth's deep history, then each cycle might leave its own set of faint, ambiguous geological fingerprints before being largely erased by the next great reset. Mathematical models of civilization survival suggest that even advanced societies are incredibly fragile over geological timescales. A civilization might rise, flourish for tens of thousands of years, and then collapse due to internal strife, environmental catastrophe, or cosmic events. If that collapse is complete, and the technological infrastructure is lost, the planet's natural processes will quickly reclaim the surface. Over millions of years, the signs of even a highly advanced society could fade into geological background noise. This is why advanced societies might not leave obvious traces. Our assumption that an ancient civilization would leave behind enduring monuments is a projection of our own cultural values onto deep time. We build pyramids and carve faces into mountains because we desire permanence. But nature's permanence is one of ongoing change and destruction. What survives are not the things we intend to preserve, but the accidental, the microscopic, the chemical, and the isotopic. The Great Reset theory posits that Earth's geological processes are so efficient at erasing information that the absence of clear, unambiguous evidence for ancient civilizations is not surprising. It is the expected outcome. It suggests that our planet is a poor archive for anything older than a few million years, particularly for the transient and fragile markers of technological societies. Therefore, the challenge is not to find a perfectly preserved ancient city, but to recognize the subtle, fragmented, and often ambiguous geological whispers that might persist after countless cycles of planetary renewal. To fully grasp the implications of the Great Reset theory, one must look beyond the grinding mechanisms of tectonics and consider the specific blind spots inherent in the formation of the geological record. The Earth does not merely bury the past, it actively curates it, and its curation criteria are heavily biased against the preservation of technological civilizations. This bias is known as the taphonomic filter, the complex set of conditions required for an organism or an object to turn into a fossil or a geological feature rather than turning into dust. The primary mechanism of this curation is the dynamic nature of coastlines. Throughout human history, and likely the history of any hypothetical predecessor, intelligent life has congregated near water. Estuaries, deltas, and coastlines offer transport, food, and cooling for industrial processes. However, these are the most geologically volatile zones on the planet. During the glacial cycles of the Pleistocene, sea levels fluctuated by over 100 meters. A civilization that flourished during the peak of the last ice age would have built its major metropolises on continental shelves that are now submerged under hundreds of feet of ocean and buried beneath millennia of sediment runoff. We are essentially looking for ruins in a graveyard that has been flooded and paved over by the silts of the Amazon, the Nile, and the Mississippi. Furthermore, the physical materials that define a high-tech society are surprisingly ephemeral. We associate durability with stone, granite and limestone monuments that can last thousands of years. But an advanced industrial civilization moves away from stone. We build with steel, glass, concrete, and composites. These are materials of high utility but low geological persistence. Iron and steel oxidize rapidly in the presence of water and oxygen, crumbling into rust, iron oxide, that becomes indistinguishable from natural red earth. Concrete, the ubiquitous skeleton of our cities, is susceptible to carbonation and sulfate attack. Within a few thousand years, it disintegrates into gravel and sand. Glass devitrifies, turning back into opaque silica. Plastic, often cited as our eternal legacy, eventually fragments into microparticles that are consumed by bacteria or sequestered into sedimentary layers where heat and pressure revert them into waxy hydrocarbons. Therefore, the Great Reset suggests that the more advanced a civilization becomes, the less likely it is to leave a recognizable structural footprint. A Stone Age culture leaves megaliths and flint tools that survive for millions of years. A Silicon Age culture leaves microchips and hard drives that rot into unrecognizable, rare earth sludge within a geological blink. This paradox implies that the absence of advanced ruins is not evidence of absence, but a consequence of the material physics of high technology. We are looking for the wrong kind of ghosts. Another critical eraser is the biological reset. The biosphere is a relentless recycling engine. Fungi, bacteria, and plants are ruthlessly efficient at breaking down complex organic and inorganic structures to reclaim nutrients. If a civilization were to perish, the forest would reclaim its cities with startling speed. Roots shatter concrete. Vines pull down transmission towers. But the biological reset goes deeper. It involves the rewriting of the genetic code. If an ancient civilization engaged in genetic engineering, creating crops, livestock, or biological tools, those modifications would eventually drift. Natural selection would aggressively prune back artificial traits that required high energy or specific maintenance. Over 1 million years, a genetically modified supercrop would either go extinct or revert to a wild-type form indistinguishable from its ancestors. The fingerprint of the designers would be washed away by the chaotic recombination of DNA, leaving only junk DNA, or viral insertions that modern geneticists might dismiss as random evolutionary noise. We must also consider the glacial eraser. The periodic advance of ice sheets acts as a planetary bulldozer. During the major glaciations, ice sheets kilometers thick scour the continents, grinding bedrock to flour and erasing all surface features. In the northern hemisphere, any evidence of civilization north of the 40th parallel from before the last glacial maximum has been effectively sanded off the map. The debris is pushed into terminal moraines, piles of jumbled rock and mud where a shattered skyscraper would look no different than a shattered mountain. This means that vast stretches of the planet are periodically wiped clean of history, leaving only the tropical zones and the deep ocean as potential, albeit difficult archives. The Great Reset theory also intersects with the concept of unconformities in geology, gaps in the rock record where time is missing. The most famous is the Great Unconformity, found in the Grand Canyon and across the world, where 1.2 billion years of rock is simply gone, eroded away before the next layer was deposited. This is 1 billion years of planetary amnesia, entire evolutionary epochs, and potentially entire civilizations could have risen and fallen within that missing billion years, and not a single atom of evidence would remain on the continents. They would have been ground into sediment and subducted. The geological record is not a continuous book. It is a few torn pages scattered on the floor of a burning library. However, the theory implies that the reset is not just mechanical, it is thermodynamic. Civilizations are islands of low entropy, order, in a universe of increasing entropy, disorder. Maintaining a city, a machine, or a data archive requires a constant input of energy. Once that energy input ceases, once the civilization collapses, the second law of thermodynamics takes over with vengeance. Corrosion, erosion, diffusion, and decay act to maximize entropy. A microchip is a highly ordered arrangement of silicon and gold. Nature wants it to be a disordered scattering of atoms. The reset is simply the planet returning to a state of thermodynamic equilibrium. To find evidence, we must look for things that are thermodynamically stuck, materials that require immense energy to create and are chemically stable enough to resist the slide back into disorder. This brings us to the nuclear shadow. While radioactive isotopes decay, the scarring they leave on the geological matrix can be permanent. Fission tracks, microscopic tunnels burned into crystal lattices by high-energy particles, can survive for hundreds of millions of years in minerals like zircon and apatite. If an ancient civilization used nuclear power or weapons, these crystals would bear the invisible scars of that era. A geologist looking at a zircon crystal from the Triassic under an electron microscope might see a density of fission tracks that exceeds background radiation levels by orders of magnitude. This would not be a structure in the traditional sense, but it would be irrefutable proof of a high-energy event that does not match natural patterns. Yet, the most profound implication of the Great Reset is the psychological barrier it creates. We operate under a linear view of history. Simple leads to complex, primitive leads to advanced. The reset theory suggests a cyclical view. Complexity is a fragile state that inevitably crashes back to simplicity. This is a terrifying prospect because it implies that progress is not a permanent ladder, but a temporary spike. If the Earth resets every few 100 million years, then we are not the culmination of history, but merely the current tenants of a property that is periodically condemned and renovated. This perspective forces us to reconsider what we mean by intelligence. We assume intelligent life builds durable structures, but perhaps true long-term intelligence understands the reset. Perhaps a civilization that survived multiple resets would abandon the futile effort of building stone monuments and steel cities. They might adapt to the cycle, developing technologies that are biological, biodegradable, and ephemeral, civilizations that leave no trace, not because they are primitive, but because they are wise. They might live within the biosphere rather than on top of it, their artifacts indistinguishable from nature itself. In that case, the lack of evidence is not a sign of their absence, but a sign of their success. They didn't get erased. They just didn't write on the wall in the first place. If we are to find the others, we must look off-world. The Earth is a self-cleaning oven. The Moon, Mars, and the asteroids are freezers. The Great Reset applies only to geologically active bodies. A stray probe, a mining outpost, or a dump site on the Moon would sit undisturbed for billions of years, protected from water, wind, and tectonics. The librarian of Earth's history is not Earth itself, it is the Moon. If we are serious about testing the reset theory, our archaeology must become astrobiology. We must scour the lunar regolith not just for helium-3, but for the glint of ancient titanium or the spectral signature of refined alloys. Ultimately, the Great Reset theory is a lesson in humility. It reminds us that our skyscrapers are temporary, our roads are fleeting, and our plastic will eventually be oil again. The planet is a dynamic, living entity that does not tolerate static scars. We are writing our history in sand at low tide. The water will come back. The only question is whether we can learn to read the ripples in the sand before the next wave washes them away, recognizing that the smooth surface of the beach is an illusion, concealing a history of castles built and destroyed over and over again in the deep, silent rhythms of geological time. The silence of the universe might not be because we are alone, but because the lifespan of a loud civilization is shorter than the blink of a geological eye, and the Earth is very, very good at hiding the bodies. Across the globe, megalithic sites defy conventional dating and construction capabilities. These are not merely large stones. They are precisely cut, impossibly heavy blocks, often fitted with a degree of accuracy that confounds modern engineering. Take Pumapunku in Bolivia, for instance. Its intricate H-shaped blocks made of hard andesite are cut with such precision that they interlock without mortar, resembling prefabricated components. The stone itself is incredibly difficult to work, yet these blocks exhibit tool marks suggesting a level of technology far beyond the known capabilities of the Tiwanaku culture, to whom the site is conventionally attributed. The dating of Pumapunku is also controversial, with some geological and archaeoastronomical analyses suggesting a much older origin, potentially predating 10,000 BCE, long before established timelines for complex human societies in the Americas. Similarly, the massive stone walls of Sacsayhuaman in Peru feature colossal boulders, some weighing over 100 tons, intricately fitted together in a zigzag pattern with paper-thin gaps. The official explanation attributes this to the Inca, who are known for their impressive stonework, but the scale and precision often lead researchers to question if they built upon an even older, pre-existing foundation. These structures showcase an understanding of engineering, geometry, and stone cutting that seems out of place for their assigned historical periods. Beyond land, the ocean holds its own mysteries. Off the coast of Yonaguni, Japan, lies a submerged rock formation that some argue is a colossal monument with steps, terraces, and carved features. While many geologists contend it is a natural formation, its geometric regularity and sharp angles, including what appears to be a triangular depression and a perfectly straight trench, lead others to believe it is an artificial structure, submerged by rising sea levels. If artificial, its age could stretch back thousands or even tens of thousands of years. Other underwater structures like the Bimini Road in the Bahamas are similarly debated. These anomalies force us to confront the possibility of advanced ancient engineering that current historical narratives cannot accommodate. The dating controversies surrounding these sites are often fierce. Conventional archaeology relies on established timelines and known technological progressions. When a site presents evidence of advanced techniques far earlier than expected, it creates a paradigm clash. New findings, such as advanced carbon dating techniques or underwater sonar mapping, continually challenge these established timelines, pushing back the potential origins of certain structures. The question is not just how these were built, but when. If these impossible structures are indeed far older than currently accepted, they would point to a sophisticated, technologically capable civilization that existed long before the dawn of recorded history. The mystery of impossible structures extends far beyond the enigmatic ruins of the Andes or the submerged anomalies of the Pacific. To fully grasp the magnitude of this historical disconnect, one must turn their gaze to the sands of Egypt, not merely to the Great Pyramids, which have been debated ad infinitum, but to the obscure subterranean vaults that contain artifacts of baffling precision. The Serapeum of Saqqara serves as a profound case study in lost industrial capability. Buried deep within a limestone bedrock tunnel system lie over 20 granite boxes or sarcophagi, each weighing roughly 70 to 100 tons. These are not rough-hewn coffins, they are triumphs of metrology. The boxes are hewn from single blocks of rose granite and black basalt, materials with a Mohs hardness of 6 to 7, far harder than the copper or bronze tools historically attributed to the dynastic Egyptians. The sheer logistics of moving such mass into a confined underground tunnel system is a nightmare for modern structural engineers, yet the true anomaly lies in the internal surfaces. When analysed with precision instruments, the inside corners of these boxes reveal a perfect 90-degree angle, machined to a tolerance that would be acceptable in a modern aerospace laboratory. A standard automotive feeler gauge cannot fit between a modern precision square and the interior wall of these ancient stone containers. To achieve such flatness and orthogonality requires a surface plate, a reference standard of extreme accuracy, and a method of grinding that removes material uniformly across a vast surface area. Hand polishing with sand and stone cannot practically achieve this geometric perfection across a consistent plane. It invariably creates subtle undulations. The existence of the Serapeum boxes implies the use of powered machinery, rigid, distinct mechanical guidance, and a sophisticated understanding of flatness that vanishes from the archaeological record for thousands of years. This evidence of machining becomes even more undeniable when examining the cores left behind by ancient drills. At the site of Abu Sir and in the Petrie Museum in London, there are granite cores, cylindrical waste products from a hollow drill, that exhibit spiral grooves. Sir William Flinders Petrie, the father of modern Egyptology, analysed these grooves and calculated the feed rate of the drill, the distance the drill bit advanced into the rock with each revolution. The calculations were staggering. The drill was sinking into solid granite at a rate of roughly 2.5 millimeters per revolution. For context, modern diamond-tipped core drills, spinning at high RPMs, advance much slower to prevent overheating and breakage. To achieve a feed rate of 2.5 millimeters in granite implies an immense downward pressure, likely in the range of tons, combined with a tool hardness capable of cutting quartz crystals without dulling instantly. Petrie himself, baffled by the physics, suggested the use of jewel-point teeth set in bronze saws, but even this does not fully explain the speed of the cut. It suggests a lost technology of sonic or ultrasonic drilling, where the tool bit vibrates at high frequency to disintegrate the stone, a method we only recently mastered in the 20th century. Moving from the micro to the macro, the impossible nature of these structures is also defined by the global consistency of their architectural style, specifically polygonal masonry. This technique, characterized by irregular interlocking stones with no mortar, is most famous in Peru, but it is not unique to the Americas. We see the exact same construction method in the ancient walls of Delphi in Greece, the fortress of Sasvad in India, and the megalithic foundations of the Temple Mount in Jerusalem. The fingerprint is identical. Massive multi-ton blocks cut into bizarre, non-uniform shapes that fit together so tightly a razor blade cannot pass between them. From an engineering standpoint, this is far more difficult than building with uniform rectangular bricks. Each stone must be individually shaped to fit its neighbours in 3 dimensions. Why go to this trouble? The answer is seismic resilience. When an earthquake strikes, a wall of uniform bricks will crack and collapse along the stress lines of the mortar. A polygonal wall, however, acts like a dynamic puzzle. The stones rattle and shift, distributing the seismic energy through the complex friction of their joints, and then settle back into place. The fact that this specific, highly complex and labour-intensive anti-seismic technique appears on continents separated by vast oceans, attributed to cultures that supposedly never met, hints at a diffusion of knowledge from a common antecedent source. It suggests a standard operating procedure for a global civilization that prioritised long-term durability over ease of construction. Further deepening the mystery is the presence of metal clamps. In Tiahuanaco, Ollantaytambo, Angkor Wat and Egypt, we find peculiar T or hourglass-shaped indentations carved into the tops of megalithic blocks. These are keystones intended to hold the stones together. However, the stones are often missing, leaving only the voids. In instances where the clamps have been recovered or analysed, they were made of metal. The architectural implication is standard reinforcement, but the metallurgical implication is anomalous. To create a tight fit, the metal would need to be poured into the indentation while molten. In South America, some of these clamps were found to be alloys requiring incredibly high melting points, temperatures achievable in a blast furnace, but difficult to maintain in a primitive open fire. Moreover, the use of iron or complex alloys in eras theoretically limited to copper or soft bronze disrupts the timeline of metallurgical evolution. We must also confront the monoliths of Baalbek in Lebanon. Here, forming the foundation of the Roman Temple of Jupiter, lie the trilithon stones, 3 limestone blocks each weighing approximately 800 to 1,000 tons. Nearby, still in the quarry, is the Stone of the Pregnant Woman, weighing an estimated 200 tons, and a recently discovered third block that may exceed 600 tons. The official narrative suggests the Romans moved these. While the Romans were brilliant engineers, their known crane technology, the polyspaston, had a lifting capacity of roughly 60 tons when used in clusters. Moving a 1,000-ton block requires a completely different magnitude of power. To drag such a stone on rollers would require a roadbed of unrealistic strength to prevent the rollers from being crushed into the earth, and a workforce so large that coordination would become impossible. The fact that the Roman temple built atop these stones is constructed of much smaller, manageable blocks suggests a regression in capability. The Romans utilised a pre-existing platform, the impossible foundation of a culture that commanded forces we can barely simulate today. The impossible nature of these sites is not just structural, it is acoustic. The Halsaflieni Hypogeum in Malta is a subterranean Neolithic structure carved from limestone. Its oracle chamber possesses acoustic properties that defy chance. A male voice chanting at a frequency of 110-111 Hz resonates throughout the complex, creating a standing wave that physically vibrates the bodies of those inside. Neuroscientific studies have shown that exposure to this specific frequency shifts brain activity from the left, prefrontal cortex, logic, to the right, creative, emotional, and can induce trance-like states. Similarly, the barrows of England and the chambers of the Great Pyramid seem tuned to specific frequencies. The Grand Gallery in the Great Pyramid, with its corbelled walls, acts as a massive acoustic amplification chamber. Was this intentional? If so, it implies an understanding of the physiological effects of sound, psychoacoustics, that was integrated into the very architecture of their holiest sites. They were not just building tombs, they were building machines for consciousness. In India, the Kailasa temple at Ellora represents an impossible subtraction. Unlike built structures, this temple was carved top-down out of a single volcanic basalt cliff. The builders removed an estimated 400,000 tons of rock. The precision required is unfathomable. There is no room for error. If a worker strikes too hard and cracks a pillar, the entire monolithic integrity is ruined. There are no mortar joints to hide mistakes. The intricate carvings, the bridges, the rain gutters, and the multi-story pillars were all envisioned in the negative space before a single chisel struck stone. The time-motion studies for this removal, assuming the traditional attribution of just 18 years of construction, would require the removal of 60 tons of rock every day, rain or shine, without powered machinery, while simultaneously carving intricate art. The logistics of debris removal alone are staggering. The site looks less like a manual sculpture, and more like the result of large-scale directed excavation technology. Furthermore, we must consider the vitrified forts of Scotland and the broader phenomenon of vitrified stone. Throughout Europe and parts of the Middle East, there are ancient stone walls that have been fused into glass. The heat required to melt granite and turn it into obsidian-like glass is roughly 1100 to 1300 degrees Celsius, sustained for long periods. A simple wood fire cannot achieve this deep, penetrating heat across massive ramparts. Theories range from lightning strikes, statistically impossible for the distribution, to deliberate destruction by enemies. But to burn a stone fort to the point of liquefaction requires a fuel source and a draft mechanism that resembles an industrial kiln or a weapon of intense thermal output. It is an anomaly of thermodynamics that remains unsatisfactorily explained by the accident theory. Finally, the sheer hardness of the materials used in these impossible structures points to a specific lost utility. Why work with granite, basalt, and diorite? These are hellishly difficult to cut. Limestone and sandstone are abundant and easy to shape. If the goal is simply to pile rocks to make a monument, soft stone suffices. The choice of granite, an igneous rock high in quartz crystal, suggests that the material properties were the point. Granite is piezoelectric. It generates an electric charge under stress. The massive granite obelisks of Egypt, often weighing hundreds of tons and transported hundreds of miles from Aswan, are essentially single crystals of conductive stone. Were they merely symbolic sun rays, or did they serve a function within a grid of energy that we no longer perceive? The impossible structures are termed as such only because we insist on viewing them through the lens of a linear technological progression. We assume that because they didn't have the internal combustion engine, they had no power. We assume that because they didn't have steel, they couldn't cut hard rock. But the evidence, the tool marks, the tolerance, the acoustics, and the materials suggests a different branch of physics or a different application of mechanics. Perhaps they mastered the manipulation of sound, vibration, and gravity in ways that our combustion-based civilization has overlooked. These sites stand as silent, stubborn witnesses to a capability gap. They are the black boxes of a crashed flight, containing data that contradicts the official accident report. To replicate the Great Pyramid, or the walls of Sacsayhuaman today, would require the mobilization of our entire global industrial capacity, and even then the results might lack the enduring finesse of the originals. We are living in the ruins of giants, attributing their work to tribes with copper chisels because the alternative, that we are a civilization suffering from amnesia, wandering the wreckage of a superior past, is too unsettling to accept. The stones do not lie, only our interpretation of them does. Imagine a cosmic event so dramatic it could scorch planetary surfaces, leaving indelible electrical scars, and yet be largely forgotten by conventional science, only to linger in humanity's oldest myths. This is the core of the plasma event hypothesis. Evidence for ancient plasma events comes from various sources, ranging from geological formations to the very surface features of planets and moons. On Earth, unexplained vitrified forts, where stone has been melted into glass, are found in Scotland and elsewhere. While often attributed to intense fires, the sheer scale and complete vitrification suggest temperatures far exceeding conventional burning. These could be localized evidence of powerful electrical discharges. More compellingly, advocates of this hypothesis point to the striking similarities in surface features across various celestial bodies. Planetary scientists have observed what appear to be electrical scarring on the surfaces of Mars, the Moon, and even Jupiter's moon Europa. These features, such as perfectly circular craters with raised rims, sinuous rills, and vast smooth plains, are often attributed to impacts or volcanism. However, proponents of the plasma hypothesis argue that these patterns are more consistent with large-scale electrical discharges, akin to enormous lightning bolts, occurring between celestial bodies or within powerful cosmic plasma streams. These events, they suggest, could have dramatically reshaped planetary surfaces. The relationship to ancient myths and legends is a crucial component of this hypothesis. Many cultures around the world share myths of celestial catastrophes, sky gods wielding thunderbolts, and periods of intense cosmic chaos. From the Vedic descriptions of Indra's weaponry to the Greek myths of Zeus's lightning, the imagery of powerful electrical forces from the heavens is pervasive. Proponents argue that these are not mere metaphors but folk memories of actual plasma events witnessed by early humans. Scientific models of plasma catastrophes explore how intense bursts of cosmic plasma, perhaps from solar flares or even passing comets, could interact with a planet's magnetosphere and atmosphere, leading to global electrical discharge events. Such phenomena could generate immense heat, powerful electromagnetic pulses, and widespread atmospheric ionization, potentially causing vitrification, atmospheric changes, and even geological upheaval. The impact on geological and archaeological records would be profound. A plasma event could instantaneously melt rock, alter the composition of surface materials, and even create unique isotopic signatures. It could also explain the sudden disappearance of entire ecosystems or early civilizations, leaving behind only ambiguous geological traces or, in the case of vitrified forts, seemingly impossible archaeological anomalies. The plasma event hypothesis, while controversial, offers a radical alternative to conventional explanations for some of Earth's unexplained geological features and ancient myths, suggesting a cosmic force that could have shaped our world in ways we're only just beginning to consider. To delve deeper into the plasma event hypothesis, one must look beyond the physical scars of the Earth and turn toward the silent testimony etched into stone by human hands. A central pillar of this theory is the global consistency of ancient petroglyphs. Across every continent, from the American Southwest to the Australian outback, from the caves of France to the valleys of Armenia, archaeologists have catalogued tens of thousands of rock carvings that depict the exact same abstract symbols. The most famous of these is the squatter man, a stick figure with a torso, raised arms, and legs bent outwards. Conventional anthropology interprets this as a shamanistic dancer or a stylized hunter. However, plasma physicists, most notably Dr. Anthony Perrott of Los Alamos National Laboratory, have offered a startlingly different interpretation. When high-energy plasma discharge occurs in a laboratory setting, specifically within a Z-pinch apparatus, it creates a column of ionized gas that undergoes predictable, morphing instabilities. As the electrical current intensifies, the plasma column buckles and forms a stack of toroids, donut shapes. Viewed from a two-dimensional perspective, specifically from the ground looking up, this three-dimensional plasma structure looks identical to the squatter man. The arms and legs are the edges of the lower and upper toroids glowing intensely due to synchrotron radiation. As the instability evolves, the structure changes, forming shapes that match other universal petroglyphs, the ladder, the duck, and the concentric circle. The plasma event hypothesis suggests that early humans were not drawing hallucinations or cultural rituals. They were recording a terrifying, towering reality in the sky, a massive glowing plasma column connecting the Earth to the heavens, perhaps the physical origin of the axis mundi or world tree found in nearly every mythology. This connection implies that the Earth's magnetosphere, which normally protects us from solar wind and cosmic rays, was at some point overwhelmed or compressed to the point of failure. In this scenario, the auroras would not have been confined to the poles. Instead, they would have descended toward the equator, intensifying into a writhing, chaotic funnel of light and radiation. This sky grid would have been visible to everyone on Earth simultaneously, explaining why the same symbols appear in rock art globally, dating to roughly the same epoch. The thunderbolts of the gods were not brief flashes of lightning as we know them, but sustained, continent-spanning arcs of electrical fire that could last for days or weeks, accompanied by a deafening, trumpeting roar, a sound often described in eschatological texts as the voice of God or the blowing of horns. The geological implications of such a cosmic thunderbolt extend far beyond surface vitrification. We must consider the mechanism of electric discharge machining, EDM. In modern industry, EDM is used to cut through hard metals by eroding them with rapid electrical sparks. Proponents of the plasma event hypothesis argue that we see evidence of planetary-scale EDM on Earth. The Grand Canyon, for instance, presents a conundrum for the standard slow water erosion model. The Colorado River is often deemed insufficient to have carved such a massive, complex feature, particularly given the uplift of the Kaibab Plateau. An electrical explanation suggests that a massive interplanetary discharge arcing between the Earth and a passing charged body, such as a cometary tail or a coronal mass ejection, could scour the surface like a cosmic router. Such an event would create Lichtenberg figures, fractal branching patterns that are the signature of electrical breakdown in solids. When we look at aerial photography of river networks, specific mountain ranges and canyon systems, the resemblance to these fractal lightning scars is uncanny. Unlike water, which follows gravity and erodes over millions of years, an electrical arc rips material away instantly, vaporizing rock and leaving behind steep, clean walls and a lack of debris at the outflow, features that puzzle geologists in certain canyons. This process would also explain the presence of spherules, microscopic balls of molten rock found in soil layers associated with extinction events. While often attributed to asteroid impacts, these spherules are also a predictable byproduct of electrical vaporization, where molten rock cools rapidly in the atmosphere before raining down. Furthermore, the hypothesis creates a bridge between the geological and the biological. A plasma event of this magnitude would bathe the planet in distinct radiation spectra. Laboratory experiments have shown that exposing biological organisms to specific electromagnetic fields and plasma environments can trigger rapid genetic mutation. This offers a radical mechanism for the punctuated equilibrium observed in the fossil record. Sudden leaps in evolutionary complexity that Darwinian gradualism struggles to explain. The Great Dying, or the sudden emergence of new species, might not be solely due to climate shifts or asteroid impacts, but the result of a radiolytic event that scrambled the DNA of the biosphere, killing the weak and mutating the survivors into new forms. We must also consider the atmospheric aftermath. A massive electrical exchange between Earth and the solar wind, or another body, would strip away parts of the atmosphere or, conversely, collapse a water vapor canopy, leading to the torrential rains often described in great flood myths. The ionization of the atmosphere would create a reddish, gloomy sky, blocking the sun for years, a purple dawn, or a chaotic darkness that persisted until the electrical equilibrium was restored. This altered atmospheric chemistry could lead to the sudden deposition of nitrates and carbon, fertilizing the soil for a rapid regrowth of flora, or poisoning it, depending on the chemical makeup of the plasma stream. The psychological trauma of such an event would be embedded in the collective unconscious of the species. Velikovsky and later researchers coined the term collective amnesia to explain why humanity has forgotten these events. Just as a trauma victim blocks out a horrific accident, the human race may have sublimated the memory of the sky falling into safe, ritualized myths. The obsession with building pyramids and obelisks, shapes that mimic the stable forms of plasma discharge, could be seen as an attempt to ground the erratic forces of the sky or to memorialize the shape of the gods. The rigid social hierarchies that emerged at the dawn of civilization, often centered around a king who could control the weather or speak to the sky, may have been a direct sociological response to the terror of a plasma catastrophe. If the sky can kill you at any moment, you willingly submit to any authority that claims to have a line of communication with it. Moreover, the plasma event hypothesis challenges the standard model of the solar system's history. Standard accretion theory posits a gravity-dominated, slow formation of planets. The electric universe model, which underpins the plasma hypothesis, suggests that the solar system is a dynamic, high-energy environment where planets are charged bodies moving through a plasma-filled heliosphere. If the electrical potential between planets changes due to orbital realignments or solar output fluctuations, discharge is inevitable. This suggests that the stable solar system we see today is merely a temporary lull in a chaotic high-voltage dance. The craters on the Moon and Mars, often perfectly circular and aligned in chains, catenae, defy the randomness of impact theory. An electrical arc moving across a surface naturally strikes at a 90-degree angle, creating circular craters regardless of the angle of approach, and can hop in a straight line, carving crater chains that meteors cannot. The search for evidence also leads to the atomic level. Transmutation of elements, once the domain of medieval alchemy, is a known phenomenon in high-energy plasma physics. Intense electrical discharges can alter atomic nuclei, theoretically turning one element into another, or creating isotopic anomalies. If a plasma event struck a specific region, it might create inexplicable concentrations of rare Earth elements, or isotopes of carbon and beryllium that mess up our radiometric dating clocks. This could mean that our timeline of history, dependent on the steady decay of radioactive isotopes, might be fractured. A massive discharge could reset the atomic clock of a rock layer, making it appear millions of years older or younger than it actually is. Finally, this hypothesis reframes our current existential risks. We worry about asteroids and climate change, but we rarely build infrastructure resilient to a Carrington-level event, let alone the kind of prehistoric Z-pinch catastrophe suggested here. If the Sun is the cathode and the heliosphere the anode of a galactic circuit, a surge in that circuit could trigger a recurrence. The Carrington event of 1859 fried telegraph wires with a relatively minor solar flare. A true plasma event, of the scale that might have vitrified the Scottish forts or carved the Martian rills, would induce currents in the Earth's crust that would vaporize modern power grids, explode transformers, and potentially trigger massive piezoelectric earthquakes. The plasma event hypothesis, therefore, is not merely a story about the past, it is a warning about the volatility of our electric environment. It suggests that we live in a universe that is connected not just by the tenuous threads of gravity, but by the thick conductive cables of plasma. The myths of dragons breathing fire, of swords falling from heaven, and of cities consumed by brimstone may be the only records we have of the last time the voltage became too high. By ignoring the electromagnetic nature of the cosmos, we may be blinding ourselves to the mechanics of the very events that shaped our planet, our evolution, and our deepest fears. The sky, in this view, is not an empty vacuum, but a waiting ocean of energy, and we are sailing on a very fragile raft. If we are to recognize traces of a technological society in the deep past, we must first understand what its lasting signatures might be, beyond crumbling cities or corroded machines. While most physical artifacts would vanish, certain industrial waste products possess remarkable resilience against the ravages of time. For instance, the enduring nature of some industrial byproducts, particularly those related to mining and manufacturing, could offer clues. Slag heaps, the glassy waste material left over from smelting ores, are surprisingly durable. If an ancient civilization engaged in large-scale metallurgy, vast quantities of slag might exist, buried in geological layers, appearing as anomalous, vitrified rock formations. These would be distinct from naturally occurring volcanic glass, and could be identified through their specific chemical composition and structure. Similarly, the widespread use of certain elements in industrial processes could leave behind unusual concentrations in sediment layers. For example, if an ancient society extensively mined and refined rare earth elements for advanced technologies, their unique isotopic signatures might be found in concentrations that defy natural geological processes. While metallic artifacts would largely corrode and return to their ore state, certain highly stable metals like gold or platinum could survive as isolated fragments or as unusual metallic inclusions in ancient rock. More perplexing are the possibilities of plastics or other synthetic polymers. Although modern plastics degrade, some forms could, under specific burial conditions, persist for millions of years, perhaps breaking down into microparticles or leaving unique chemical residues that are not easily explained by natural organic decomposition. The mystery of ancient high technology then becomes a question of recognizing these subtle, chemical, and microscale signatures. We are not looking for an intact smartphone, but perhaps for unusual concentrations of rare metals or complex hydrocarbon polymers in geological layers that predate the known origin of such materials. The challenge lies in distinguishing these potential technological fingerprints from natural geological phenomena or biological processes. Why certain artifacts survive while others don't is a matter of material science and geological context. Materials that are chemically stable, resistant to erosion, and buried quickly in an atoxic environment have the best chance of preservation. A gold figurine encased in rapidly deposited oxygen-poor sediment, for example, might survive far longer than a steel beam exposed to the elements. Therefore, the search for lost technology signatures requires a shift in perspective, from expecting grand monuments to meticulously analysing anomalous chemical and isotopic patterns, understanding that the most enduring legacies of an ancient civilization might be found not in what they built, but in the subtle ways they altered the very chemistry of their planet. Beyond the immediate residue of industrial production, the slag, the plastics, and the refined metals, lies a deeper, more esoteric category of evidence, the signature of fundamental physics manipulation. If a civilization advances sufficiently, it inevitably moves from manipulating matter on a macro scale, building walls, to manipulating it on an atomic or subatomic scale. The resulting artifacts are not objects in the traditional sense, but statistical anomalies in the atomic record, deviations from the universal baseline that can only be explained by intelligent intervention. One of the most potent of these signatures is the nuclear shadow. While the half-lives of many radioactive isotopes are short, the daughter products, the stable elements into which they decay, remain forever. We must consider the implications of a global nuclear industry, or a conflict involving high-yield weaponry. A detonation or a reactor meltdown releases a specific cocktail of isotopes that does not occur in nature. For instance, the ratio of cesium-137 to strontium-90 is a distinct marker of fission events. While these specific isotopes decay within centuries, they decay into barium and zirconium, respectively. A geologist analysing a thin layer of clay from the Eocene period might find a localised, inexplicable spike in barium and zirconium with isotopic ratios that perfectly match the decay chain of a fission event. Nature produces these elements, but not in those precise paired ratios, and certainly not concentrated in a global fallout layer. Furthermore, we must look for the extinct isotopes. Plutonium-234 is a primordial isotope with a half-life of 80 million years. It existed when Earth was formed, but has effectively decayed into non-existence over 4.5 billion years. If we were to find a trace of plutonium-244 in a rock layer that is only 50 million years old, it would present a massive paradox. It could only come from a supernova occurring dangerously close to Earth, which would leave other astronomical evidence, or from artificial synthesis. Finding young plutonium in an old world is the chronometric equivalent of finding a fresh footprint in ancient concrete. Then there is the matter of technical ceramics and synthetic gemstones. Humans currently produce vast quantities of synthetic sapphire, aluminum oxide, for use in electronics, watch faces, and military armour. Unlike glass, which is amorphous and unstable over geological time, sapphire is crystalline and incredibly hard, Mohs 9. It is chemically identical to natural sapphire, but structurally it is flawless. Natural gemstones have inclusions, gas bubbles, cracks, and impurities that act as a birth certificate of their chaotic formation in the Earth. Synthetic crystals are often perfect, or they contain specific trace elements used to dope the crystal for conductivity, like silicon wafers. If a sediment core yielded a microscopic dust of perfectly pure, inclusion-free aluminum oxide spheres, it would suggest a manufacturing process, specifically the use of abrasives or heat-resistant coatings. These micro-artifacts would not erode, they would simply settle, forming a gemstone horizon that sparkles under a spectrometer but looks like sand to the naked eye. Another persistent signature would be the manipulation of the carbon cycle, specifically regarding nanomaterials. We are currently entering the age of graphene and carbon nanotubes, These materials are sheets of carbon atoms arranged in hexagonal lattices, possessing immense strength and conductivity. Carbon is naturally abundant, but carbon nanotubes, specifically single-walled varieties, are not a standard product of geology. While some fullerenes, buckyballs, can form in lightning strikes or wildfires, the long cylindrical structure of a nanotube is thermodynamically unlikely in nature. These structures are chemically inert. They do not rot. A layer of sediment containing a high concentration of multi-walled carbon nanotubes would suggest a society that mastered the molecular assembly of carbon. Over millions of years, these might not remain as functional wires, but their unique chicken wire atomic structure would be detectable via Raman spectroscopy. They would be the microskeletons of an advanced materials science. We must also consider the concept of geochemical sequestering. An advanced civilization, realizing the damage it is doing to its atmosphere, might attempt to sequester carbon dioxide or other pollutants on a massive scale. This goes beyond simple tree planting. We are talking about mineral carbonation, injecting CO2 into basalt formations to turn it into solid carbonate rock. This process creates a very specific type of rock, rapid growth carbonates with an isotopic signature that matches the atmosphere of the time, not the ocean. Finding a massive, geologically instantaneous deposit of carbonate rock that is isotopically light, rich in carbon-12 from fossil fuels, and located deep inland within basaltic traps would look like a natural anomaly, but it would actually be a planetary engineering project, a landfill for the sky. Similarly, the depletion of specific resources creates a negative signature. Nature distributes elements based on chemical affinity. Gold, for example, is often found in hydrothermal quartz veins. If an ancient civilization mined the earth efficiently, they would have removed the easy-to-reach, high-grade ores, leaving only the diffuse, low-grade background levels. A future geologist might be puzzled by a metal drought, a geological period where the expected natural concentrations of copper, tin, or gold in the crust are statistically missing from the accessible surface layers. The ore gap would be a silent testament to a hunger that consumed the planet's crust. We see this already. We are mining grades of copper today that would have been considered waste rock a century ago. A society that exhausted the planet would leave a crust that is chemically depleted of free metals, forcing any subsequent civilization to rely on recycling or asteroid mining. The search for lost technology also intersects with the field of paleogenetics, but not in the search for bones. We should look for chiral anomalies. Amino acids, the building blocks of life, possess a property called chirality. They are handed. Life on Earth exclusively uses left-handed L-form amino acids. Industrial chemistry, however, when synthesizing amino acids in a lab, typically produces a racemic mixture, a 50-50 split of left and right. If a mass extinction event was accompanied by a sediment layer rich in racemic amino acids, it would imply that the biomass was not just dying, but that a significant portion of the organic matter was synthetic in origin. It would be the chemical signature of a world where the distinction between grown and made had blurred. Furthermore, we must consider the ultimate storage medium, the crystal lattice. If a civilization wished to leave a message that would survive not just thousands but millions of years, they would not write on paper or carve in stone. They would etch data into the heart of a stable crystal. We are currently developing 5D optical data storage in quartz glass, capable of withstanding high temperatures and surviving for billions of years. Such a crystal would look like a pebble. It would be indistinguishable from a piece of river glass until struck by a laser. The signature here is not the object itself, but its optical properties. A quartz crystal that diffracts light in a non-random binary pattern would be a Rosetta Stone disguised as gravel. The challenge is that we would never think to shine a laser through a random rock found in a coal seam. Finally, there is the signature of biological standardization. A global civilization homogenizes the biosphere. We transport crops and livestock across oceans, creating a Pangea of utility. The pollen record of the Anthropocene is defined by the sudden, global dominance of Zea maize, corn, and triticum, wheat. In a deep time context, we should look for pollen spikes where a single highly productive plant species suddenly appears on all continents simultaneously, defies climatic zones, and then vanishes. This would not be invasive evolution, which is slow and chaotic. It would be agriculture. The genetic uniformity of such a plant, if DNA fragments could be recovered, would be the clincher. Nature loves diversity. Clones are the hallmark of industry. a layer of rock containing the fossilized pollen of a monoculture that spanned from the equator to the temperate zones would be evidence of a global food network. The detection of these signatures requires a paradigm shift from hunting to forensics. We are not looking for the gun, we are looking for the gunshot residue. The evidence is likely microscopic, isotopic, and statistical. It is hidden in the ratio of boron in ancient clays, indicative of detergents and borosilicate glass, in the traces of gadolinium in river deltas, indicative of MRI contrast agents and medical tech, and in the presence of exotic phases of ice or high-pressure minerals formed not in the mantle, but in the crucible of a laboratory. The implications of finding such signatures are profound. It would mean that the ladder of progress is actually a wheel. It would validate the cyclical view of history found in so many ancient traditions, but more importantly, it would serve as a mirror. If we find that a previous civilization collapsed despite, or because of, their mastery of the atom, their synthesis of life, and their engineering of the planet, it reframes our own current crisis. We are currently laying down these exact layers. We are creating the uranium halo, the plastic horizon, the chicken wire carbon layer, and the racemic spill. We are writing the very text that we are trying to read in the past. Therefore, the study of lost technology signatures is not merely an archaeological exercise, it is a survival strategy. By identifying the indelible marks of a failed industrial state, we might learn to distinguish between the growing pains of a civilization and the terminal symptoms of one about to extinguish itself. The Earth is a hard drive that has been overwritten many times, but the magnetic ghost of the previous data remains for those with the sensitivity to read the noise between the sectors. We must look at the rock not as a solid mass, but as a frozen fluid that caught the chemical breath of the world as it was. And in that breath, we might smell the ozone of ancient machines. Beyond the debated structures and chemical fingerprints, the Earth itself presents a myriad of geological anomalies that challenge conventional explanations and could, under a different paradigm, hint at something extraordinary. These are not always grand, easily recognizable features, but often subtle, out-of-place formations or unusual material compositions that defy straightforward geological interpretation. For instance, there are numerous accounts of unexplained formations and structures found deep within rock strata, far older than any known human activity. These include perfectly spherical metal or stone objects, recovered from coal seams dating back millions of years, or intricate metallic threads found embedded in geological layers that should contain only primitive organic matter. While often dismissed as concretions or natural mineral formations, their geometric regularity and often metallic composition spark persistent curiosity. Evidence of ancient mining operations, dating back hundreds of thousands or even millions of years, also falls into this category. While hominids certainly used tools to extract resources, the scale and sophistication suggested by some deep earth excavations or the precise removal of certain ore bodies in ancient geological contexts raise questions. For example, some researchers point to unusually precise extraction patterns in ancient gold or copper deposits that seem to go beyond what primitive tools could achieve or appear in layers far too old for known human activity. Mysterious geological processes, too, are sometimes invoked to explain away these anomalies. For example, unusual rock formations that appear to be carved or shaped are often attributed to weathering and erosion, even when the patterns seem unnaturally precise. The concept of out-of-place artifacts, OOPArts, is central to this discussion. These are objects of apparent human manufacture found in geological contexts that would place them millions of years before the accepted timeline of human evolution. Examples range from ancient hammerheads found in Cretaceous rock to intricate jewellery discovered in coal seams. While many OOPArts have been debunked or reinterpreted as natural formations, a persistent few continue to defy easy explanation. They challenge the very foundation of evolutionary and archaeological timelines, suggesting that complex tool-making or even advanced craftsmanship existed far earlier than we currently believe. Scientific attempts to explain these anomalies often involve invoking rare geological conditions, misidentification, or even hoaxes. However, the sheer volume and diversity of these unexplained findings, when considered collectively, begin to form a pattern of persistent irregularities. If we assume that Earth's history might include multiple intelligent species, Then these geological anomalies and new parts transform from mere curiosities into potential fragments of a lost past, challenging us to expand our understanding of what is possible within the deep history of our own planet. The oceans, vast and deep, serve as the ultimate repository of Earth's history, their sediments holding a layered chronicle of millennia. Unlike the terrestrial record, which is constantly eroded and recycled, deep ocean sediments can accumulate undisturbed for immense periods, offering an unparalleled memory of water. Analysing these ocean sediment records has revealed profound changes in ancient ocean chemistry that often align with major environmental shifts. For instance, shifts in oxygen isotope ratios can indicate past temperature fluctuations, while changes in carbonate levels point to ocean acidification events. However, some of these changes are unusually abrupt or extreme, hinting at forces beyond typical natural cycles. Here, the concept of industrial pollution in prehistoric times becomes particularly intriguing. If an ancient civilization discharged industrial waste into the oceans, or if a global catastrophe associated with such a civilization impacted marine ecosystems, its chemical signature could be preserved in these deep-sea layers. For example, unusual concentrations of heavy metals, microplastics, or their ancient equivalents, or specific isotopic ratios of elements like nitrogen or carbon, could be indicative of widespread industrial activity. These would appear as anomalous spikes or persistent changes in the chemical composition of sediment cores, defying explanation by known natural processes. Furthermore, marine archaeological anomalies occasionally surface, albeit rarely due to the immense scale and difficulty of deep-sea exploration. While not directly linked to prehistoric industrial pollution, discoveries of unexplained structures, unusual artifacts, or even peculiar patterns on the seafloor suggest that human or intelligent activity might have left traces in the marine environment far older than conventionally accepted. The ocean, with its unique preservation conditions, could act as a time capsule for the remains of a civilization. Materials quickly buried in anoxic, cold, deep-sea sediments can be preserved for far longer than their terrestrial counterparts. While buildings would still collapse and metals would corrode, their chemical traces or even highly resilient synthetic materials might persist as a faint layered record. The memory of water, therefore, offers a unique and largely unexplored avenue for seeking evidence of ancient civilizations, providing a continuous, albeit subtle, archive of planetary change that could hold the chemical echoes of a lost technological past. Beyond the cold, hard data of geology and chemistry, humanity's oldest stories and sacred texts offer another, more ephemeral, yet equally potent source of information: the collective memory embedded in myths. While often dismissed as mere fantasy, ancient texts from diverse cultures around the world frequently describe advanced civilizations, catastrophic global floods, and technical knowledge that seems out of place for their supposed historical context. Many ancient texts, such as the Hindu Vedas, the Sumerian King List, or the Egyptian Turin Papyrus, speak of long-reigning dynasties and gods who possessed extraordinary knowledge and advanced technologies. These accounts often detail periods of immense progress followed by devastating cataclysms. While interpreted as allegories or divine interventions, could some of these narratives be distorted memories of actual advanced societies that existed in distant antiquity? The most pervasive and striking commonality in ancient myths is the global flood narrative. Cultures from nearly every continent, from the Epic of Gilgamesh to the biblical Genesis, from Native American legends to Aboriginal Dreamtime stories, recount a time when a great deluge swept across the earth, wiping out almost all life. While geological evidence for a single global flood event is lacking, the universality of these myths suggests a shared memory of widespread devastating inundations. Could these be folk memories of massive sea level rises, perhaps triggered by rapid climate change or even the collapse of ice sheets at the end of an ice age, events that would have profoundly impacted coastal civilizations? Furthermore, some ancient writings appear to contain technical knowledge that seems surprisingly sophisticated. The Piri Reis map, an Ottoman map from 1513, shows remarkably accurate coastlines of Antarctica long before its official discovery and details that suggest knowledge of its pre-ice sheet geography. The Vimanas described in ancient Indian texts are often interpreted as flying machines, while descriptions of advanced weaponry in various myths hint at destructive power beyond conventional ancient warfare. While these interpretations are controversial, they prompt the question, are these mere coincidences, or are they echoes of a forgotten technological past? Oral traditions passed down through generations are incredibly resilient. While details change over time, the core narrative often persists. When these oral traditions speak of geological correlations, such as descriptions of landscapes that are now submerged or events that align with known periods of geological upheaval, they gain a new layer of credibility. Modern interpretation of ancient accounts, therefore, requires a willingness to look beyond literal translations and consider the possibility that these myths contain fragments of historical truth encoded in symbolic language. If an advanced civilization existed before us, its memory would likely be preserved not in concrete ruins, but in the enduring narratives that shape human culture, serving as a subtle, yet persistent, reminder of a lost past. The idea of a prior intelligent civilization on Earth often encounters significant academic resistance, a phenomenon rooted in the very nature of scientific paradigms. Mainstream science, by its design, operates within established frameworks, and evidence that challenges these foundational assumptions is typically met with skepticism, if not outright dismissal. This is not necessarily a conspiracy, but rather a reflection of how scientific progress often works. New ideas must overcome significant inertia to be accepted. How mainstream science handles anomalous evidence is a critical point. When an artifact or a geological signature appears to contradict established timelines or understanding, the initial response is usually to find a conventional explanation. This might involve redating the object, reinterpreting its function, or attributing it to natural processes, even if those processes are themselves rare or highly specific. The natural nuclear reactor at Oklo is a prime example, an undeniable anomaly that was ultimately explained through a highly specific and rare natural mechanism, thus preserving the existing paradigm that complex technology is a recent human invention. The history of science is replete with case studies of rejected evidence. Alfred Wegener's theory of continental drift, for instance, was initially ridiculed for decades before eventually becoming the cornerstone of plate tectonics. Similarly, the idea that meteor impacts could cause mass extinctions was once dismissed as catastrophic thinking, only to be vindicated by the discovery of the Chicxulub crater. These examples highlight the role of paradigm shifts in scientific understanding. Fundamental changes in worldview are often slow, difficult, and require overwhelming evidence to overcome entrenched beliefs. The changing face of archaeological acceptance also illustrates this dynamic. Sites like Göbekli Tepe in Turkey, dating back over 11,000 years, profoundly challenge the previous understanding of agricultural development and the origins of complex societies. Its discovery forced archaeologists to re-evaluate their timelines, pushing back the origins of monumental architecture and organised religion by thousands of years. This demonstrates that while academic resistance is real, paradigms can and do shift when confronted with irrefutable evidence. The institutional response to the Silurian Hypothesis, therefore, is crucial. While it is a thought experiment rather than a claim of discovery, it forces science to confront its own assumptions about the completeness of the geological record and the uniqueness of human intelligence. The resistance it faces is not a sign of its falsehood, but rather an indicator of how deeply ingrained our current understanding of Earth's history truly is. Much of the potential evidence for ancient civilizations might not be found in spectacular undiscovered ruins, but rather in plain sight, overlooked or misinterpreted within common geological features and already excavated archaeological sites. The problem often lies not in the absence of evidence, but in the problem of recognition. Our pre-existing biases, shaped by current scientific paradigms, dictate what we expect to find and how we interpret what we see. For instance, the very formations we attribute to natural erosion or geological processes might, in some cases, bear the faint weathered marks of intelligent design. Anomalous rock formations that appear to have geometric regularity or unusual carving patterns are often dismissed as pareidolia, the tendency to see patterns in random data. However, if we entertain the possibility of an ancient non-human civilization, then some of these formations might warrant a second, unbiased look. Similarly, reinterpreting known archaeological sites could yield new insights. Many sites, particularly those with megalithic structures or advanced engineering, are conventionally attributed to the earliest known cultures of the region, often with explanations that strain credulity regarding their technological capabilities. If we consider the possibility that these cultures inherited or built upon much older foundations, the impossible structures suddenly become less impossible. The biases that affect scientific interpretation are powerful. If a researcher expects to find only Stone Age tools in a certain geological layer, an anomalous metallic object might be dismissed as contamination, rather than being rigorously investigated as a potential OO part. The human tendency to fit new data into existing frameworks, rather than challenging the framework itself, can lead to critical evidence being overlooked or explained away. New approaches to identifying ancient civilizations are therefore needed. This involves multidisciplinary research, combining geology, archaeology, chemistry, and even advanced computational analysis to look for patterns that might escape the human eye. It means adopting a stance of epistemological humility, acknowledging that our current understanding of Earth's deep history is incomplete, and that the absence of obvious evidence does not equate to absence of existence. The key is to shift from looking for what we expect to find, to being open to recognizing what we have not yet considered possible, understanding that the most profound secrets of Earth's past may be hidden in plain sight, waiting for us to shed our conventional blinders. The absence of obvious, enduring monuments from a hypothetical ancient civilization does not necessarily mean such a civilization never existed. Instead, it might imply that their technology reached a certain technological threshold, where its impact on the geological record became subtle or even intentionally ephemeral. This concept, the technological threshold theory, suggests that an advanced civilization might not leave the kind of permanent physical traces we expect. One aspect of this theory explores why advanced civilizations might not leave obvious traces. Perhaps their technology became so efficient, so integrated with natural systems, or so focused on non-material forms of existence, that its physical footprint was minimal. Imagine a civilization that mastered advanced forms of energy entirely renewable and clean, perhaps even developing technologies that could decompose waste products back into their constituent elements, leaving no lasting pollution. Such a society would leave a far smaller and less recognizable geological signature than our own. The concept of technological singularity, often discussed in the context of future AI, can also be applied to ancient contexts. If an ancient civilization reached a point where its intelligence and technology advanced exponentially, its methods of construction, resource extraction, and waste management might have become so sophisticated that they left little to no lasting archaeological or geological evidence. How technology affects geological footprints is crucial. Our current industrial civilization is leaving a massive observable footprint. Carbon emissions, plastic pollution, concrete structures, and nuclear waste. But if a past civilization developed green or invisible technologies, its impact would be far harder to detect over deep time. A society that used biodegradable materials, recycled all resources perfectly, or even developed energy sources that left no chemical trace would effectively erase itself from the future geological record. This opens the possibility of non-industrial advanced civilizations. We tend to equate advanced with industrial because that is our own trajectory. But an ancient civilization might have developed along entirely different technological paths, perhaps mastering biology, energy fields, or consciousness in ways we cannot yet comprehend. Their technology might not involve factories and machines in our sense, but rather a profound understanding and manipulation of natural forces that leaves no conventional archaeological signature. New models for recognizing technological societies, therefore, must move beyond the expectation of ruins and artifacts. They must consider the subtle, indirect evidence, anomalous energy signatures, highly specific and localized geological alterations, or even disruptions to natural biological cycles that cannot be fully explained by conventional means. The technological threshold. Theory suggests that the more advanced a civilization becomes, the less noise it might leave in the geological record, making its detection a profound challenge for future investigators. The vastness of Earth's deep history, combined with the planet's relentless geological cycles, opens the door to a compelling idea. that intelligence and civilization might not be a singular event, but a recurring pattern, a series of Earth's cycles of civilization. Mathematical models of civilizational rise and fall often suggest that societies, even advanced ones, are inherently unstable over long periods. Factors such as resource depletion, environmental degradation, internal conflict, or external catastrophic events can lead to collapse. If such collapses are complete and the knowledge base is lost, a new civilization might arise much later, unaware of its predecessors. This implies that evidence for recurring advanced societies might not be easily recognizable as a continuous progression, but rather as distinct, ephemeral spikes in the geological record, separated by immense gulfs of time. The role of catastrophic events in civilization cycles is particularly significant. A major asteroid impact, a supervolcanic eruption, or a rapid extreme climate shift could easily wipe out an advanced society, leaving behind only fragmented evidence or even accelerating the geological erasure of its existence. The very events that mark geological boundaries, often seen as purely natural, could potentially coincide with the endpoints of such lost civilizations. Geological indicators of societal collapse, therefore, might be found in layers associated with sudden environmental shifts, abrupt changes in atmospheric chemistry, or unusual sedimentation patterns that defy typical natural processes. For example, a sudden spike in specific heavy metals or unique isotopic ratios coinciding with a period of rapid climate change could be interpreted as the aftermath of an industrial civilization's collapse. By examining patterns in Earth's deep history, we might begin to identify these cyclical echoes. Are there recurring anomalous layers in the geological record that suggest repeated non-natural interventions? Do certain chemical signatures appear multiple times, separated by tens or hundreds of millions of years, hinting at repeated industrial activity? The concept of Earth's cycles of civilization shifts our perspective from a linear human-centric view of progress to a more cyclical, planetary-scale understanding of intelligence. It suggests that our current moment might not be a unique pinnacle, but merely one iteration in a grand, repeating drama of rise, transformation, and eventual erasure, played out over billions of years on the ever-resetting stage of Earth. The conventional narrative of Earth's past, while robust, is built upon a specific set of interpretations and assumptions. Yet there exist compelling alternative Earth histories, theories that challenge these established timelines and open up radical new possibilities for the story of intelligence on our planet. Competing theories about Earth's past often arise from anomalous data points that do not fit neatly into the prevailing paradigm. For instance, the uniformitarian view of geological change, which posits slow, gradual processes, is increasingly challenged by evidence of catastrophism, suggesting that sudden, violent events have played a far more significant role in shaping Earth's history than previously acknowledged. This shift in understanding opens the door for the possibility of rapid civilization-ending events that would leave little trace. New models of human civilization development, such as those inspired by Göbekli Tepe, suggest that complex societies and monumental construction might have emerged much earlier than once thought, forcing a re-evaluation of the timelines for human technological advancement. If humans were capable of such feats 11,000 years ago, what might other intelligent species have achieved millions of years prior? Evidence that challenges conventional timelines often comes from out-of-place artifacts or geological anomalies that defy easy explanation. These range from ancient maps depicting accurate pre-Ice Age coastlines to metallic spheres found in coal beds. While each can be individually dismissed, their cumulative effect is to chip away at the certainty of our established historical framework. The role of catastrophism in Earth's history is a crucial element of these alternative narratives. If Earth has experienced numerous global cataclysms, massive asteroid impacts, supervolcanic eruptions, or even plasma events, then the geological record would be inherently fragmented and discontinuous. Such events could repeatedly wipe the slate clean, erasing evidence of previous civilizations and making it nearly impossible to reconstruct a continuous history of intelligence. Integrating new findings with established science is the ongoing challenge. It requires an open mind, a willingness to re-examine long-held assumptions, and a commitment to following the evidence wherever it leads, even if it disrupts comfortable narratives. Alternative Earth histories, therefore, are not merely speculative. They are a necessary intellectual exercise, urging us to consider that the story we tell ourselves about our planet and our place within its deep history might be far less complete and far more astonishing than we ever imagined. If the evidence of ancient civilizations is subtle, fragmented, and prone to geological erasure, then the search for it demands a methodological shift, moving beyond traditional archaeological digs to embrace modern techniques for identifying ancient civilizations across vast timescales. New archaeological dating methods are continually refining our ability to pinpoint the age of materials. Techniques like optically stimulated luminescence, OSL, can date sediments that have been exposed to light, while thermoluminescence dating can determine the last time a mineral was heated. These methods, combined with improvements in radiocarbon dating and other isotopic analysis, allow for more precise dating of anomalous finds, pushing back the boundaries of what was once considered possible. Advanced geological analysis tools are equally crucial. Ground-penetrating radar, GPR, LiDAR, and satellite imagery can now reveal buried structures or unusual geological formations that are invisible from the surface. Seismic surveys, typically used in oil exploration, can map deep subsurface structures, potentially identifying anomalous patterns that might suggest ancient engineering. Geochemical analysis of sediment cores, employing mass spectrometry and other highly sensitive techniques, can detect the minute chemical and isotopic anomalies that might constitute the geological fingerprints of past industrial activity. The role of artificial intelligence in pattern recognition is rapidly becoming indispensable. AI algorithms can sift through vast datasets of geological, chemical, and satellite imagery, identifying subtle patterns, correlations, and anomalies that would be impossible for human researchers to detect. AI could be trained to recognize the specific chemical signatures of ancient industrial waste, the geometric regularities of deeply buried structures, or the statistical improbability of certain elemental concentrations in ancient strata. Future directions in prehistoric research will undoubtedly involve a convergence of these technologies. It will require interdisciplinary teams of geologists, archaeologists, chemists, physicists, and AI specialists working together. The search will shift from expecting grand, obvious ruins to meticulously analysing the planet's chemical and geological memory, seeking the faint, almost imperceptible echoes of past intelligence. It is a search for whispers in the noise of deep time, guided by advanced technology and an open mind, constantly questioning the boundaries of what we think we know about Earth's long and complex history. The implications of finding definitive evidence of earlier civilizations on Earth would be nothing short of revolutionary, shattering deeply held assumptions and forcing a profound re-evaluation of humanity's place in the cosmos. It would fundamentally change our understanding of humanity, moving us from a singular, unique event to potentially one iteration in a grand, cyclical pattern of intelligence. The comfort of being first would vanish, replaced by the unsettling possibility that our own civilization is merely a fleeting moment in a much larger, older story. The impact on current scientific theories would be immense. Evolutionary biology would have to grapple with the repeated emergence of advanced intelligence. Geology would need to re-examine countless natural anomalies for potential artificial origins. Archaeology and anthropology would be forced to completely rewrite the timelines of technological and societal development. Cosmology too might be affected, as it would suggest that intelligence is not as rare as often assumed, at least within a planetary context. Future research directions would explode in scope. The search for ancient civilizations would become a primary scientific endeavor, leading to new methods, new technologies, and a global effort to re-examine every anomalous finding. Funding would pour into multidisciplinary projects aimed at deciphering the geological and chemical record for clues. The philosophical implications of non-uniqueness are perhaps the most profound. If intelligence has risen and fallen before, it challenges our anthropocentric view of the universe. It forces us to confront our own fragility and the impermanence of even the most advanced societies. It might lead to a deeper understanding of the environmental and societal pitfalls that could have led to past collapses, offering crucial lessons for our own survival. The very definition of progress would be questioned. and our sense of specialness would be replaced by a humbling awareness of being part of a potentially recurring cosmic drama. Moving beyond the current paradigm, therefore, is not just about finding evidence. It is about embracing a new worldview, one that acknowledges the vastness of time, the fragility of evidence, and the profound possibility that the story of intelligence on Earth is far older, stranger, and more complex than we were ever taught to believe. The journey through Earth's deep past reveals a landscape far more complex and uncertain than often portrayed. We began with the uncomfortable question: what if we are not the first intelligent species on Earth? This question, once considered mere speculation, has gained scientific traction through the Silurian Hypothesis, which meticulously outlines how a prior industrial civilization could have existed and then largely vanished from the geological record. The core argument rests on the understanding that geological time is an aggressive grinder, relentlessly erasing physical evidence. Only the most subtle and resilient chemical and isotopic signatures, or the most robust and precisely placed structures, might persist for millions of years. We examined the key evidence, the unexplained nuclear isotope ratios of the Ocklo phenomenon, which demonstrated that nuclear fission occurred naturally 2 billion years ago, shattering assumptions about technological thresholds. We explored chemical anomalies, sudden dramatic shifts in carbon and nitrogen isotopes, and unexpected synthetic compounds in ancient rock layers that mirror the industrial pollution of our own age. We reconsidered mass extinctions, particularly the Permian event, asking if some of their unusual features could be linked to ancient civilizational collapse rather than purely natural causes. The Great Reset theory highlighted Earth's continuous geological recycling, explaining why advanced societies might leave no obvious traces. We looked at impossible structures, megalithic sites, and underwater formations that defy conventional dating and engineering, suggesting a forgotten past. The plasma event hypothesis offered a cosmic explanation for widespread electrical scarring and ancient myths. We considered what lost technology signatures might look like, not intact machines, but persistent industrial waste products, and how geological anomalies and ooparts challenge established timelines. Finally, the memory of water in ocean sediments and the echoes of advanced knowledge in ancient myths provided further tantalizing clues. Evaluating these arguments, we see that while no single piece of evidence offers definitive proof, their cumulative effect is to erode the certainty of our anthropocentric timeline. The strongest arguments lie in the convergence of geological plausibility, chemical anomalies, and the sheer vastness of deep time, which makes our current understanding of intelligence's singularity statistically improbable. Proposals for future research must involve a radical interdisciplinary approach, leveraging advanced AI for pattern recognition in geological data, meticulous geochemical analysis of anomalous layers, and a critical re-examination of existing archaeological and geological sites without preconceived biases. The changing nature of scientific certainty is perhaps the most profound takeaway. We're moving from a position of confident knowing to one of humble not knowing. This is not a failure of science, but a moment of intellectual honesty, acknowledging the vast gaps in our understanding of Earth's past. The philosophical implications are immense. If intelligence is not unique to humanity, it forces us to confront our own place in the universe, to learn from potential past failures, and to consider a future where our own civilization might one day become just another whisper in the geological record. Our final thoughts on human civilization's place in time must therefore be one of profound humility and open-minded inquiry. The history of intelligence on Earth may be far older, stranger, and more cyclical than we ever dared to imagine, urging us to rewrite the chapters of our past with a pen guided by curiosity rather than certainty. The idea that advanced civilizations could have risen and fallen before humanity, leaving behind barely a trace, is not merely a fringe theory. It's a thought experiment that challenges the very foundations of archaeological and geological interpretation. This concept, often dubbed the Silurian Hypothesis, suggests that if an industrial civilization existed millions of years ago, the evidence of its presence would be incredibly subtle, easily overlooked, or completely eradicated by the relentless processes of deep time. We are talking about a scale of time so vast that continents reshape, mountain ranges erode into plains, and entire ocean basins open and close. In such a colossal span, what truly endures? Consider the sheer destructive power of geological forces. Tectonic plate movements subduct crustal material, effectively recycling the Earth's surface. Imagine a city built on a continental plate. Over tens of millions of years, that plate could be pushed beneath another, melting back into the Earth's mantle, taking all traces of the city with it. Volcanic eruptions bury landscapes under layers of ash and lava, creating new surfaces that would seal away any previous structures. Erosion, driven by wind and water, relentlessly grinds down everything exposed to the elements. Even the most robust modern structures, like skyscrapers and dams, are not designed to withstand geological epochs. Concrete crumbles, steel rusts, and plastics degrade. What might remain of our current civilization after 50 million years? Perhaps a thin, chemically anomalous layer in the sedimentary record, a scattering of unusually shaped mineral formations, or perhaps nothing at all recognizable as artificial. The fossil record itself offers a compelling analogy. While we find bones and shells, which are relatively durable, the vast majority of life forms, particularly soft-bodied creatures, leave no fossilized remains. For an industrial civilization, the primary evidence would not be biological in the traditional sense, but technological. Yet, technology is often ephemeral. Think about the components of a modern computer or smartphone. They are composites of various materials, many of which are designed for functionality, not geological longevity. Silicon chips, plastic casings, and delicate wiring would quickly disintegrate under natural conditions. Even durable materials like concrete and steel would eventually succumb to weathering and geochemical reactions. So if we were looking for an ancient industrial civilization, what exactly would we be searching for? Direct artifacts would be exceedingly rare. Instead, scientists propose looking for indirect techno-signatures in the geological record. These are anomalies that would be difficult to explain by natural processes alone. One such techno-signature could be unusual isotopic ratios. Industrial processes often concentrate specific elements or alter their isotopic balance. For example, the burning of fossil fuels releases carbon with a distinct isotopic signature. An ancient industrial civilization might have left behind layers of sediment with anomalous carbon isotope ratios, or perhaps unusual concentrations of heavy metals that are typically dispersed in nature but are byproducts of industrial activity. Another potential techno-signature could be artificial materials that are geologically persistent. While plastics degrade, some synthetic polymers or ceramics might persist for extraordinary lengths of time, especially if buried and protected from surface weathering. The discovery of microscopic, unusually uniform spheres of a synthetic material, or a layer of an unidentifiable non-biological polymer, might raise questions. However, proving their artificial origin after millions of years would be an immense challenge, as natural geological processes can also create complex and seemingly ordered structures. Furthermore, the very concept of industrial might need to be broadened. An ancient civilization might not have relied on the same energy sources or material technologies as our own. Perhaps they harnessed geothermal energy, or developed bioengineered materials that are now indistinguishable from natural organic compounds. This introduces a significant bias. We are naturally inclined to look for evidence that mirrors our own technological development. The true nature of an ancient advanced civilization could be so alien to our current understanding that we wouldn't recognize its traces even if we stumbled upon them. The ocean floor presents another fascinating yet equally challenging frontier for this search. Submerged cities, if they existed, would be subject to immense pressure, corrosive seawater, and deposition of vast amounts of sediment over millions of years. While the deep sea preserves some ancient shipwrecks remarkably well, these are only a few thousand years old. Multiply that by thousands, and the picture changes dramatically. Any structures would likely be buried under kilometers of sediment, making detection and excavation extraordinarily difficult. Moreover, the ocean floor itself is constantly being renewed at mid-ocean ridges and consumed at subduction zones, further reducing the chances of long-term preservation. Consider the implications for our understanding of planetary habitability. If Earth has hosted multiple, independent intelligent civilizations over its 4.5 billion year history, it suggests that the emergence of intelligence might not be as rare as we currently believe. This would profoundly impact the Fermi paradox. which questions why we haven't found evidence of extraterrestrial life. Perhaps the universe is teeming with life, but civilizations are often short-lived, or their techno-signatures are too transient to be detected across vast cosmic distances, or even across deep time on a single planet. The Great Filter, the hypothetical barrier that prevents civilizations from becoming interstellar, might lie not in the difficulty of life emerging, but in the difficulty of a civilization surviving long enough to leave an undeniable, enduring mark on its home planet, let alone expand beyond it. The Silurian Hypothesis also forces us to re-evaluate our archaeological methods. Traditional archaeology focuses on the Holocene and Pleistocene epochs, periods spanning hundreds of thousands of years. But if we are looking for evidence from the Eocene or the Cretaceous, we need different tools and different perspectives. We would need to integrate geological and paleontological techniques more intimately with archaeological thinking. This means analysing core samples from deep ocean sediments and ice, scrutinising ancient soil layers for chemical anomalies, and developing new methods for detecting highly degraded or subtly altered artificial materials. It requires an interdisciplinary approach that transcends the usual boundaries of scientific fields. One of the most intriguing aspects of this thought experiment is its potential to reshape our understanding of Earth's climate history. An ancient industrial civilization would undoubtedly have had an impact on its planet's environment, just as ours is having on Earth today. Could some unexplained climate anomalies in the geological record be attributed to such a civilization? For instance, periods of rapid, unexplained warming or cooling, or sudden shifts in atmospheric composition might be re-examined through this lens. If an ancient civilization caused a self-inflicted climate catastrophe, the evidence might be preserved in ice cores or sediment layers as shifts in oxygen isotopes or carbon dioxide levels. However, distinguishing these from natural climate fluctuations would be incredibly complex, requiring sophisticated modelling and robust correlation across multiple geological proxies. The very concept of what constitutes intelligence and civilization also comes under scrutiny. Do we define it by tool use, by complex social structures, by the ability to modify the environment on a large scale, or by the development of abstract thought and communication? If a non-human species, perhaps one with a radically different biology and cognitive structure, developed a civilization, its manifestations might be entirely unlike anything we would expect. Imagine a civilization of highly intelligent burrowing creatures that built vast subterranean networks, or an aquatic species that engineered complex underwater habitats. Their techno-signatures would be vastly different from ours and might be even harder to detect or interpret. The challenge lies in avoiding pareidolia, the tendency to perceive meaningful patterns in random data. It's easy to look at an unusual rock formation and imagine it's an ancient ruin, or to interpret a natural geochemical anomaly as an industrial byproduct. The scientific method demands falsifiability and rigorous evidence. For any potential technosignature, countless natural explanations must be ruled out before an artificial origin can even be considered. This is where the humility comes in. It's not about jumping to conclusions, but about maintaining an open mind to possibilities while adhering to the higher standards of scientific proof. This deep time perspective also offers a sobering lesson for our own civilization. If previous advanced species have risen and fallen, leaving little behind, it underscores the fragility of even the most sophisticated societies. It suggests that sustainability is not just an ethical imperative, but a practical necessity for long-term survival. The environmental impact of our current industrial age could be seen as a grand experiment, the outcome of which will determine whether humanity leaves a lasting, recognizable mark on the geological record, or if we too will eventually fade into a barely perceptible whisper in the strata. The implications extend beyond science into philosophy and even existential questions. If we are not the first, then what can we learn from those who came before? Did they face similar challenges, environmental collapses, or internecine conflicts? Could their failures provide a cautionary tale, a guide to navigating the perilous waters of technological advancement and global impact? The very search for these lost civilizations becomes a reflection on our own trajectory, a way to understand our potential pasts and possible futures. It transforms the Earth from a passive backdrop to human history into a dynamic archive, holding secrets that could redefine our place in the universe. The quest for these ancient echoes demands not just better tools, but a profound shift in perspective, a willingness to gaze into the deep past with an imagination unfettered by anthropocentric biases. The very notion of a prior intelligent species forces us to confront the Silurian Hypothesis, a thought experiment popularized by scientists Adam Frank and Gavin Schmidt. This hypothesis challenges the conventional assumption that if advanced civilizations existed on Earth, we would find abundant, unmistakable evidence. Instead, it posits that industrial civilizations might leave a surprisingly ephemeral footprint on geological timescales. Imagine our own industrial age, with its sprawling cities, vast networks of roads, and immense energy infrastructure. While seemingly permanent to us, these structures are incredibly vulnerable to the relentless forces of erosion, tectonic plate movement, and biological decomposition over millions of years. A city made of concrete and steel exposed to the elements for even a few 100,000 years would likely be reduced to rubble, its materials reintegrated into the Earth's crust. The Great Wall of China, an engineering marvel, would eventually be just another ridge, its bricks and mortar indistinguishable from natural rock formations after sufficient geological time. Consider the energy signatures of such a civilization. We currently burn fossil fuels, releasing carbon dioxide into the atmosphere, which leaves a discernible isotopic signature. A prior industrial civilization might have done the same, or perhaps used nuclear power, leaving behind specific radioactive isotopes. These traces, however, could be deeply buried, altered by geological processes, or even diluted beyond recognition over vast stretches of time. The challenge lies in distinguishing these potential technosignatures from natural geological anomalies. For instance, an unusually high concentration of a certain metal could be a natural ore deposit, or it could be the remnants of an ancient industrial process. The ambiguity is profound, demanding sophisticated analytical techniques and a willingness to interpret data through a new lens. The deep time perspective is crucial here. Our species, Homo sapiens, has only existed for roughly 300,000 years, and our industrial civilization for a mere 300 years. The Earth, however, is 4.5 billion years old. This immense chasm of time means that even if an advanced civilization existed for hundreds of thousands of years, or even a million years, it would still represent a fleeting moment in Earth's history. To put it in perspective, if Earth's history were compressed into a single 24-hour day, human civilization would barely register as a flicker in the last second. Any evidence left by such a fleeting presence would be incredibly difficult to detect, especially if it predated the Cenozoic era, the geological epoch we currently inhabit. The further back in time we look, the more geological processes have had to erase, bury, and transform any potential evidence. Geological processes are not merely destructive, they are also transformative. Tectonic plate subduction, for example, can drag entire continental crusts, along with anything built upon them, deep into the Earth's mantle, effectively recycling them. Volcanic eruptions can bury landscapes under hundreds of feet of ash and lava, preserving some things but utterly obliterating others. Erosion by wind and water can wear down mountains and fill in valleys, constantly reshaping the Earth's surface. These forces act relentlessly, over timescales that are almost incomprehensible to the human mind. The challenge, then, is not just to find something, but to find something that has survived these immense geological forces relatively intact, and that is also recognizably artificial. The potential technosignatures we might look for are diverse. Beyond chemical anomalies in the atmosphere or geological strata, we could consider unusual patterns in the fossil record. Perhaps a sudden, inexplicable extinction event that doesn't align with known natural causes could point to an environmental catastrophe caused by a prior civilization. Or perhaps the sudden appearance of certain mineral formations that are not naturally occurring or occur in unusual concentrations could be the remnants of industrial waste products or construction materials. We might even look for highly ordered structures, like unusually geometric arrangements of rocks or subsurface anomalies that defy natural explanation. The key is to think beyond our current technological capabilities and imagine what an incredibly advanced, or perhaps even an alien, civilization might leave behind. Their technology might be so different from ours that we wouldn't even recognize its remnants as artificial. One of the greatest hurdles in identifying evidence of a prior intelligent species is our inherent anthropocentric bias. We tend to look for things that resemble our own civilization: ruins, tools, written language. However, an advanced civilization, particularly one that existed millions of years ago, might have developed in ways we cannot easily comprehend. Their technology might not be based on the same principles as ours, their societal structures might be entirely different, and their impact on the planet could manifest in ways we haven't yet considered. This bias can blind us to subtle clues, causing us to dismiss potential evidence as natural phenomena or geological oddities. Consider the concept of biomarkers in the search for extraterrestrial life. We look for oxygen, methane, and other gases that are indicative of life as we know it. But what if life on another planet, or even ancient life on Earth, developed along entirely different biochemical pathways, producing entirely different biomarkers? The same principle applies to technosignatures. We might be looking for a smoking gun in the form of a perfectly preserved artifact, when the true evidence lies in a subtle, widespread, and deeply integrated alteration of the planet's geology or atmosphere. The problem is compounded by the fact that our understanding of Earth's deep past is itself incomplete. We are constantly discovering new species, new geological processes, and new interpretations of ancient events. Our knowledge of the fossil record, for example, is far from exhaustive. It is a fragmented tapestry with vast stretches missing. This incompleteness means that any anomalous findings could easily be attributed to unknown natural processes rather than to the actions of a prior intelligence. The burden of proof for an artificial origin is incredibly high, requiring compelling evidence that cannot be explained by any known natural phenomenon. Furthermore, the very definition of intelligence and civilization can be anthropocentric. We tend to associate intelligence with tool-making, complex language, and large-scale architectural feats. But what if an ancient intelligent species developed forms of communication or societal organization that left no comparable physical trace? Perhaps their technology was entirely organic, or perhaps they achieved a level of integration with their environment that made their presence virtually indistinguishable from nature itself. The idea of a sustainable advanced civilization that leaves minimal impact is often discussed as a future goal for humanity. If a prior civilization achieved this, their technosignatures would be even more elusive. This challenge of recognition demands a radical shift in perspective. We need to actively search for anomalies that defy conventional explanations, and we need to be open to interpreting those anomalies through a non-anthropocentric lens. This might involve developing new analytical techniques to detect extremely subtle, chemical or isotopic signatures, or employing artificial intelligence to identify complex patterns in vast data sets of geological or atmospheric data that human observers might miss. It also requires a willingness to re-examine existing geological and paleontological findings with a fresh, open mind, questioning assumptions that have long been taken for granted. If a prior intelligent species existed on Earth, what specific traces might they have left behind that we could potentially discover? The answer depends heavily on their technological level, their lifespan, and the nature of their interaction with the planet. Let's consider a few hypothetical scenarios, moving from the most obvious to the most subtle. At the most direct level, we might look for deeply buried ruins. While surface structures would erode, subsurface constructions like tunnels, foundations, or even entire underground cities might be protected from surface erosion. The challenge here is the immense depth at which such remnants could be found, requiring advanced geological survey techniques like seismic imaging or ground-penetrating radar, applied over vast areas and at extreme depths. Even if such structures existed, identifying them as artificial amidst the complex geology of the Earth's crust would be a formidable task. Imagine trying to distinguish an ancient buried city from a naturally occurring geological formation, like a lava tube or a complex mineral vein. The geometric regularity expected of artificial structures would be the key, but even that can be mimicked by natural processes over geological timescales. Moving beyond direct structures, we could search for highly durable artifacts. While most materials decay, some are incredibly resilient. Think of ceramics, synthetic diamonds, or even certain types of highly stable polymers that might have been developed by an advanced civilization. These materials, if designed for extreme longevity, could survive for millions of years, albeit likely in fragmented or altered forms. The difficulty lies in distinguishing these from naturally occurring minerals or meteoritic fragments. a microscopic analysis revealing an unusual crystalline structure or an isotopic composition not found in nature could be a clue. The problem is that such discoveries would likely be rare and isolated, making it difficult to prove they are part of a larger intelligent design. Then there are the discarded elements, the waste products of a civilization. Our own industrial society produces unique chemical signatures: plastics, radioactive waste, heavy metal pollution. A prior civilization, depending on its technology, might have left behind similar or entirely different waste streams. For instance, the long-lived radioactive isotopes produced by nuclear fission or fusion could persist for millions of years. Finding unusual concentrations of these isotopes in ancient sedimentary layers, especially those that predate the natural formation of such elements, could be a strong indicator. Similarly, the presence of synthetic elements, or elements in isotopic ratios that do not occur naturally, could point to advanced technology. These are the kinds of technosignatures that might be detectable using advanced geochemical analysis of ice cores, deep-sea sediments, or ancient rock formations. Beyond physical objects or chemical signatures, we might look for evidence of large-scale environmental engineering. Perhaps a prior civilization altered the course of rivers, created artificial lakes, or even terraformed portions of the planet. While these changes would largely erode over time, they might leave subtle, long-lasting geological scars. For example, an unusually straight canyon or a series of precisely aligned geological features that defy natural explanation could be remnants of ancient engineering projects. These would be incredibly difficult to identify, as nature itself can create remarkably regular patterns. The evidence would need to be overwhelming, ruling out all natural formation mechanisms. Finally, we could hypothesize about information itself. Could an ancient civilization have encoded information in a durable, stable form that could survive for millions of years? Perhaps not in written texts, which would decay, but perhaps in the molecular structure of synthetic materials, or even in the genetic code of specifically engineered organisms. This is highly speculative, pushing the boundaries of what we currently understand about information storage and longevity. However, if such a civilization existed and possessed truly advanced technology, they might have foreseen the ephemeral nature of their physical structures and sought to leave a more enduring message. Detecting such a message and then deciphering it would be the ultimate archaeological challenge, requiring a level of scientific and technological advancement far beyond our current capabilities. If evidence of a prior intelligent species exists, the most likely places to find it are not on the Earth's surface, which is constantly reshaped by erosion and tectonic activity, but in realms that offer greater protection and stability, the deep ocean and subterranean environments. These hidden archives of the Earth hold immense potential for preserving long-lost secrets. The deep ocean, particularly the abyssal plains and trenches, is a remarkably stable environment. Sediments accumulate slowly and steadily, often undisturbed by the violent forces that affect continental landmasses. An object or structure that sank to the deep ocean floor millions of years ago could be gradually buried by layers of sediment, potentially preserving it for vast stretches of time. Furthermore, the low oxygen levels and cold temperatures in many parts of the deep ocean inhibit decay, offering a natural form of preservation. Imagine a deep-sea drilling expedition uncovering an anomalous, geometrically precise structure buried beneath millions of years of sediment. Or perhaps, rather than intact structures, we might find layers of unusual marine microfossils or unique chemical signatures within ancient ocean floor sediments, indicative of a civilization's impact on the marine ecosystem or its waste disposal practices. Hydrothermal vents and volcanic activity in the deep sea also offer unique opportunities. While destructive in some ways, these environments can also create conditions for rapid burial and mineralization, potentially preserving artifacts or even biogenic structures in a fossilized state. The challenge, of course, is the sheer scale and inaccessibility of the deep ocean. Exploring these vast dark realms requires highly specialized submersibles and robotic probes, and even with these tools we have only explored a tiny fraction of the ocean floor. Much of it remains a mystery, a blank canvas where untold discoveries could be hidden. Subterranean environments such as deep caves, lava tubes, and even deep mines offer another promising avenue. These spaces are protected from surface erosion, weather, and many biological processes. If a prior civilization built underground structures or used natural caves for habitation or resource extraction, their remnants could be remarkably well preserved. The geological stability of certain subterranean formations can be immense, offering protection for millions of years. Imagine a deep mining operation unexpectedly breaking into a vast, ancient and artificially constructed cavern system, revealing structures or artifacts unlike anything known to natural geology. The challenge in subterranean exploration is similar to that of the deep ocean: accessibility and scale. Many deep cave systems remain unexplored, and the technology to efficiently and non-invasively explore vast subterranean networks at extreme depths is still developing. Moreover, the very act of geological formation can obscure or destroy evidence. Tectonic shifts can collapse caves, and groundwater can fill and erode them over time. Nevertheless, the potential for discovering remarkably intact evidence in these protected environments makes them prime targets for future investigation. The key to exploring both the deep ocean and subterranean realms lies in advanced remote sensing and imaging technologies. Gravity anomaly mapping could reveal unusual subsurface densities indicative of large-scale artificial structures. Seismic tomography could image complex underground networks. Autonomous underwater vehicles, AUVs, and subterranean robots, equipped with advanced sensors, could systematically explore these environments, searching for patterns and anomalies that deviate from natural geological formations. The future of searching for lost civilizations might not involve traditional archaeological digs on land, but rather deep-sea expeditions and subterranean probes, pushing the boundaries of our exploration capabilities into the very heart of the Earth. The search for a prior intelligent species is fundamentally about interpreting anomalies. The Earth is full of strange and wondrous geological formations, unusual mineral deposits, and inexplicable fossil discoveries. The critical challenge lies in distinguishing between a truly natural anomaly and one that suggests an artificial origin. This is a fine line, fraught with the risk of pareidolia, the tendency to see patterns in random data, and the equally dangerous risk of dismissing genuine evidence as merely natural variation. Consider the example of the out-of-place artifacts, or UPARTs. Throughout history, various objects have been discovered in geological strata that seem to contradict the accepted timeline of human evolution or technological development. These range from the Klerksdorp spheres, small metallic spheres found in Precambrian rock in South Africa, to the alleged Koso artifact, a spark plug-like object found encased in a geode. While many of these have been debunked or explained by natural processes, the Klerksdorp spheres are often attributed to natural concretions, and the Koso artifact to a modern object that became encased in a rapidly forming geode. They highlight the difficulty in interpretation. The key is rigorous scientific analysis, ruling out all possible natural explanations before considering an artificial one. The burden of proof for an artificial origin is incredibly high, and rightly so. Extraordinary claims require extraordinary evidence. This means that any potential technosignature must be analysed with extreme scrutiny, using multiple independent lines of evidence. For example, if an unusual chemical signature is found, it needs to be confirmed by multiple analytical techniques, compared against known natural occurrences, and its context within the geological layers needs to be thoroughly understood. If a geometric structure is discovered, its regularity and complexity must be beyond what natural processes are known to produce, and its material composition should ideally be anomalous. The problem is that natural processes can at times mimic artificiality. Crystals can form with remarkable geometric precision. Geological fault lines can create linear features that appear almost engineered. Even biological processes can lead to highly ordered structures. Distinguishing between these natural mimics and genuine technosignatures requires a deep understanding of geology, chemistry, physics, and biology, as well as a healthy dose of skepticism. It also requires an open mind, willing to consider the possibility of the truly unexpected. Furthermore, the very act of recognizing an anomaly can be subjective. What one scientist dismisses as a geological oddity, another might see as a potential clue. This is where interdisciplinary collaboration becomes crucial. Geologists, paleontologists, chemists, physicists, and even archaeologists need to work together. bringing their diverse perspectives and expertise to bear on anomalous findings. A geologist might identify an unusual rock formation, a chemist might analyse its composition, and an archaeologist might consider its potential function if it were artificial. This collaborative approach increases the chances of both correctly identifying natural phenomena and recognising genuine techno-signatures. Ultimately, the interpretation of anomalies is an iterative process. A potential techno-signature is identified, hypotheses are formed, and further research is conducted to either confirm or refute those hypotheses. This process can take years, even decades, as new data emerges and analytical techniques improve. The search for a prior intelligent species is not about finding a single definitive piece of evidence, but rather about accumulating a body of evidence that, taken together, points overwhelmingly towards an artificial origin, defying all known natural explanations. It is a scientific detective story, played out over geological timescales, with the Earth itself as the primary archive. The discovery of a prior intelligent species on Earth would have profound ethical and societal implications, shaking the foundations of our understanding of history, humanity, and our place in the cosmos. It would not merely be a scientific revelation, it would be a paradigm shift with far-reaching consequences. Ethically, such a discovery would force us to confront our anthropocentric view of the planet. If Earth has hosted other intelligent life, then our claim to unique dominion over it, or our assumption that we are the pinnacle of evolution, would be severely challenged. It might prompt a re-evaluation of our environmental responsibilities, considering that another species might have faced similar challenges and perhaps succumbed to them. Did they exploit their planet to its detriment? Did they achieve a sustainable coexistence? Their fate could serve as a powerful cautionary tale or an inspiring example for our own civilization. Societally, the impact would be immense. Textbooks would need to be rewritten, historical narratives re-evaluated. Religions would grapple with the implications for their creation stories and the uniqueness of humanity. The very concept of human exceptionalism would be undermined. This could lead to a crisis of identity for some, but for others, it could open up new avenues of philosophical and spiritual inquiry, expanding our understanding of consciousness and intelligence. The initial reaction might be one of shock and disbelief, followed by intense debate and re-examination of our core beliefs. Economically and politically, a discovery of this magnitude could also have significant effects. The race to understand and potentially access the technology or knowledge of a prior civilization could spark new geopolitical rivalries. Who would control the research? Who would interpret the findings? Would the knowledge be shared openly, or would it become a closely guarded secret? The potential for new energy sources, advanced materials, or even medical breakthroughs from studying their remnants could be immense, leading to a new technological arms race. Furthermore, the discovery could influence our search for extraterrestrial intelligence. If Earth itself has hosted multiple intelligent species, it suggests that intelligence might be a more common phenomenon in the universe than previously thought. This could intensify efforts to listen for signals from space and to explore other planets and moons within our solar system for signs of past or present life. The implications for astrobiology would be staggering, providing a tangible example of the potential for diverse forms of intelligence to arise and evolve. The psychological impact on humanity would also be significant. Learning that we are not the first, and perhaps not the last intelligent species to inhabit Earth, could foster a sense of both humility and wonder. It might encourage a deeper contemplation of our own impermanence and our place in the grand sweep of cosmic history. It could also inspire a renewed sense of purpose, urging us to learn from the successes and failures of those who came before, to build a more resilient and sustainable future for our own species. The mere possibility of such a discovery, even without concrete evidence, already pushes us to think differently about our past and our future. It forces us to confront uncomfortable questions and to broaden our intellectual horizons. This search itself, regardless of its outcome, is a journey of self-discovery for humanity. The concept of a pre-human industrial civilization, often dubbed the Silurian Hypothesis, opens up a fascinating thought experiment. If such a civilization existed millions of years ago, what traces would it leave behind, and how would those traces differ from the geological record we currently understand? Consider the deep time involved. the Earth has undergone immense geological transformations over hundreds of millions of years. Continents have drifted, mountain ranges have risen and eroded, oceans have formed and receded, and ice ages have sculpted the very surface of the planet. Any direct evidence of buildings, tools, or even advanced technology would likely be pulverized, subducted into the Earth's mantle, or weathered into unrecognizable dust. The sheer destructive power of geological processes over such vast timescales is difficult for our human minds, accustomed to lifespans measured in decades, to fully grasp. However, the Silurian Hypothesis suggests we might not be looking for direct artifacts, but rather for more subtle, indirect signatures. Our own industrial civilization, for instance, is rapidly altering the planet's atmospheric composition, creating novel synthetic materials and distributing unique isotopic signatures through our reliance on fossil fuels and nuclear technology. These are the kinds of long-lasting fingerprints a prior civilization might have left. For example, a global industrial civilization would likely have left a carbon isotope anomaly in the geological record, similar to the one we're creating now. The burning of fossil fuels releases carbon with a distinct isotopic signature, different from naturally occurring carbon, and this signal can be preserved in sedimentary rocks. If a previous civilization had a similar energy-intensive existence, we might find a corresponding blip in ancient carbon isotope ratios. The challenge lies in distinguishing such an anomaly from natural geological events, like massive volcanic eruptions or significant changes in oceanic circulation, which can also influence carbon cycles. Furthermore, the widespread use of plastics and other synthetic materials by a technologically advanced species would introduce entirely new chemical compounds into the environment. While most plastics degrade over time, some forms, particularly microplastics, are incredibly persistent and are already being incorporated into the geological record of our own era. Imagine a layer of ancient sediment containing an unusual concentration of complex, non-biogenic polymers. Such a discovery would be highly anomalous and could point towards an artificial origin. The key would be to differentiate these from naturally occurring organic molecules, which can also be highly complex. The unique molecular structures and lack of biological precursors would be critical indicators. Another potential signature could be the presence of unusual elemental abundances or ratios. Our current technological society extracts and refines vast quantities of certain elements, like rare earth metals, copper, and iron. These elements are then distributed globally through manufacturing and trade. If a prior civilization engaged in similar activities, we might find localized enrichments or unusual elemental ratios in ancient geological formations that cannot be explained by natural geological processes. For instance, an unexpected concentration of a particular metal in a sedimentary layer, far from any known natural deposit, could be a tantalizing clue. The challenge here is that geological processes themselves can concentrate elements, making it difficult to discern an artificial signature from a natural one without a very clear anomaly. The very concept of stratigraphy, the study of layered rocks, is built on the idea that each layer represents a specific period in Earth's history. If a previous industrial civilization existed, its impact might be recorded as a distinct, anomalous layer or series of layers within this geological column. This technosignature layer could contain a confluence of the aforementioned indicators: carbon isotope anomalies, synthetic materials, unusual elemental compositions, and perhaps even microscopic remnants of engineered structures or durable tools. The difficulty lies in the fact that these layers would be incredibly compressed and altered by geological forces over millions of years, making their identification and interpretation a monumental task. We are, in essence, searching for a needle in a haystack, where the haystack itself is constantly shifting and being reformed. The search for these technosignatures requires a multidisciplinary approach, drawing on geology, chemistry, paleontology, and even astrobiology. Scientists would need to develop new analytical techniques capable of detecting subtle anomalies in ancient rock samples. This might involve advanced mass spectrometry to analyze isotopic ratios with unprecedented precision, or sophisticated imaging techniques to identify microscopic structures that are not naturally occurring. It would also require a willingness to challenge existing paradigms and to consider the possibility that some geological anomalies currently attributed to natural processes might have a different, more intriguing explanation. The scientific community, by its very nature, is often conservative, demanding extraordinary evidence for extraordinary claims. Overcoming this inherent skepticism would be a significant hurdle. Beyond the purely physical evidence, one might also consider the potential for biological technosignatures. If a previous civilization engaged in widespread genetic engineering, for example, it might have left behind modified organisms or unique genetic sequences that could be preserved in ancient DNA. While the preservation of DNA over millions of years is extremely challenging, especially in the absence of permafrost or very specific geological conditions, it is not entirely impossible. The discovery of ancient microbes with highly unusual genetic structures, or the identification of genes that seem to have no natural evolutionary lineage, could be a powerful indicator. This area of research, known as paleogenetics, is still in its infancy, but its potential for uncovering deep biological history is immense. Another fascinating avenue of exploration involves the concept of orphan technologies, technological artifacts or knowledge that appear to be far more advanced than their supposed historical context. While often dismissed as hoaxes or misinterpreted natural phenomena, some ancient artifacts like the Antikythera mechanism push the boundaries of what we believe ancient civilizations were capable of. While these are relatively recent in Earth's history, the idea itself can be extrapolated to deeper time. If a previous civilization existed and somehow managed to leave behind a few incredibly durable, complex artifacts that survived the ravages of time, they would stand out as profound anomalies. The challenge here is the sheer unlikelihood of such artifacts surviving intact over geological timescales without being completely destroyed or reabsorbed by the Earth. The implications of discovering such a civilization would extend far beyond scientific curiosity. It would fundamentally alter our understanding of life's trajectory on Earth and our place within the cosmos. The realization that intelligent life has emerged, flourished, and perhaps even vanished before us on our own planet would be a profound lesson in humility and the impermanence of even the most advanced civilizations. It would force us to confront uncomfortable questions about our own sustainability and the ultimate fate of our species. Are we destined to follow a similar path, or can we learn from the past and forge a different future? The psychological impact on humanity would be significant. Learning that we are not the first and perhaps not the last intelligent species to inhabit Earth could foster a sense of both humility and wonder. It might encourage a deeper contemplation of our own impermanence and our place in the grand sweep of cosmic history. It could also inspire a renewed sense of purpose, urging us to learn from the successes and failures of those who came before, to build a more resilient and sustainable future for our own species. The mere possibility of such a discovery, even without concrete evidence, already pushes us to think differently about our past and our future. It forces us to confront uncomfortable questions and to broaden our intellectual horizons. The search itself, regardless of its outcome, is a journey of self-discovery for humanity. The notion of a hidden, prior civilization on Earth directly connects to one of the most profound unanswered questions in science, the Fermi paradox. This paradox asks why, given the vastness of the universe and the high probability of life arising elsewhere, we haven't yet found any evidence of other intelligent civilizations. One of the most compelling explanations for the Fermi paradox is the Great Filter, a hypothetical barrier or series of barriers that prevents intelligent life from reaching an advanced interstellar stage. The Great Filter could be in our past, meaning that the emergence of intelligent technological life is incredibly rare, or it could be in our future, suggesting that advanced civilizations inevitably encounter some catastrophic event that leads to their demise. If a prior intelligent civilization existed on Earth and subsequently vanished, it would suggest that at least one part of the Great Filter lies in our future. A chilling prospect indeed. Consider the various stages where a Great Filter could operate. It could be an extremely improbable step in the abiogenesis of life itself, meaning that the spontaneous emergence of living organisms from non-living matter is far rarer than we currently assume. Or it could be a challenge in the evolution of complex multicellular life from simple single-celled organisms, a process that took billions of years on Earth. Another potential filter could be the development of intelligence from complex life, or the subsequent development of technology from intelligence. Each of these steps represents a significant hurdle, and if any one of them is sufficiently improbable, it could explain the apparent absence of extraterrestrial civilizations. However, if a prior intelligent civilization did exist on Earth and then disappeared, it would point to a great filter that occurs after. the emergence of technological intelligence. This would be a more sobering conclusion, as it would imply that even if a species reaches our current level of technological advancement, there's a significant chance they won't survive much longer. This future filter could take many forms. It could be a self-inflicted catastrophe, such as global environmental collapse due to unsustainable practices, nuclear war, or the uncontrolled development of artificial intelligence. If a previous civilization succumbed to such a fate, it would serve as a stark warning for our own future. The remnants of their self-destruction, perhaps in the form of unusual radioactive isotopes or widespread environmental toxins in ancient sediments, might be the very techno-signatures we would be looking for. Alternatively, the Great Filter could be an external threat, such as a devastating asteroid impact, a supervolcanic eruption, or a gamma-ray burst from a distant supernova. While Earth has experienced numerous extinction events throughout its history, few have been so absolute as to completely erase all traces of a global civilization, particularly one with advanced technology. However, if such an event was sufficiently powerful and coincided with a critical stage of a prior civilization's development, it could explain their disappearance. The challenge here is that most major geological and astronomical catastrophes leave distinct signatures in the geological record, which would need to be carefully analysed to see if they coincide with any potential techno-signatures. The very act of searching for these lost civilizations forces us to confront the possibility that the Great Filter might indeed be ahead of us. It compels us to consider the existential risks that our own civilization faces, and to perhaps take more seriously the need for global cooperation and sustainable practices. If a previous intelligent species on Earth faltered due to resource depletion, climate change, or internecine conflict, then understanding their demise could provide invaluable lessons for our own survival. The potential discovery of a precursor civilization would transform the Great Filter from a theoretical concept into a tangible historical event, a cautionary tale etched into the very rocks of our home planet. The implications for astrobiology would be staggering, providing a tangible example of the potential for diverse forms of intelligence to arise and evolve. It would shift our focus from merely searching for life on other planets to also contemplating the cyclical nature of intelligent life within a single planetary system. It would suggest that intelligence is not a singular event, but perhaps a recurring phenomenon, subject to the same processes of rise and fall as any other species. This perspective would fundamentally alter our understanding of the cosmic landscape, suggesting that the universe might be filled not just with emerging civilizations, but also with the ghostly echoes of those that came before. The idea of a hidden, prior intelligent species on Earth challenges our deeply ingrained anthropocentric view of the world. For centuries, humanity has largely considered itself the pinnacle of evolution, the sole intelligent species to have ever graced this planet. This perspective, while perhaps comforting, can also limit our imagination and our scientific inquiry. If we assume that we are unique, we might inadvertently overlook evidence that suggests otherwise. The very act of considering a pre-human intelligence forces us to shed some of these preconceptions and to approach the geological and paleontological records with a more open mind. Our current understanding of Earth's history is largely built on the assumption that complex technological civilizations are a relatively recent phenomenon, emerging only in the last few thousand years. This assumption is based on the archaeological record, which clearly shows the development of human societies from hunter-gatherers to agriculturalists to industrial powers. However, this record only goes back so far, and the preservation of delicate artifacts over millions of years is highly improbable. If a previous civilization existed, it would have to be incredibly ancient, predating the rise of hominids entirely. This means we wouldn't be looking for human-like artifacts, but rather for evidence of a completely different form of intelligence, perhaps one that evolved from a lineage entirely distinct from our own. Consider the vast diversity of life that has existed on Earth. Dinosaurs dominated the planet for over 160 million years, a period far longer than the entire existence of the human lineage. If intelligence is not solely tied to our specific evolutionary path, then it's conceivable that some other lineage, perhaps even one of the more successful dinosaur groups, could have developed a form of intelligence and even technology. While often relegated to science fiction, the idea of dinosauroids, or other non-mammalian intelligent species, highlights the limitations of our current anthropocentric biases. We tend to define intelligence in human terms, focusing on tool use, language, and complex social structures. But what if intelligence manifests in ways we haven't yet fully conceived? For instance, an aquatic intelligent species might develop tools and technologies that are entirely different from our own, perhaps relying on bioluminescence, sonar, or manipulating currents in ways we can barely imagine. Their cities might not be towering skyscrapers, but intricate underwater structures or living reefs that they have cultivated and engineered. The techno-signatures they leave behind would be entirely different from what we might expect from a land-based fire-wielding civilization. We would need to expand our search parameters beyond the familiar to truly encompass the possibilities. This requires a profound shift in perspective, moving away from a human-centric definition of intelligence and technological advancement. Furthermore, challenging our anthropocentric view encourages us to consider the possibility that intelligence doesn't always lead to the same outcomes. Our civilization, for example, is heavily reliant on fossil fuels and has a significant impact on its environment. But what if a previous intelligent species developed a more sustainable, perhaps even symbiotic relationship with its planet? Their technology might be less destructive, leaving behind fewer obvious scars on the geological record. They might have mastered forms of energy that leave no carbon footprint, or developed materials that seamlessly reintegrate into natural cycles. In such a scenario, the evidence of their existence would be even more subtle and harder to detect, requiring an even more nuanced approach to scientific investigation. The very act of questioning our uniqueness can also foster a deeper appreciation for the unique circumstances that led to our own emergence. It highlights the improbable chain of events that allowed our species to evolve, develop language, create technology, and ultimately contemplate our place in the universe. It underscores the fragility of our existence and the preciousness of the intelligence we possess. By shedding our anthropocentric biases, we open ourselves up to a universe of possibilities, where intelligence might be a more diverse and recurring phenomenon than we currently imagine, even within the confines of our own planet. This intellectual humility is not a weakness, but a strength, allowing us to ask more profound questions and to seek answers in unexpected places. One of the primary reasons we haven't found evidence of a prior intelligent civilization on Earth is the inherent limitations of archaeological and geological preservation over vast timescales. Our archaeological record, which documents human civilization, extends back only a few tens of thousands of years, with truly complex structures and widespread artifacts appearing even more recently. This is a mere blink of an eye in Earth's 4.5 billion year history. To find evidence of a civilization that existed, for instance, 50 million or 200 million years ago, we would need to delve into the realm of geology, where the processes of erosion, sedimentation, plate tectonics, and metamorphism constantly reshape the planet's surface. Imagine a city as grand and enduring as any human metropolis existing 100 million years ago. Over such an immense period, entire mountain ranges would have risen and fallen, oceans would have opened and closed, and continents would have drifted thousands of kilometers. The very rock upon which that city was built would likely have been subducted into the Earth's mantle, melted, and recycled. Even the most durable materials we create today, like concrete and steel, would eventually succumb to weathering, erosion, and chemical decomposition. The forces of nature are relentlessly destructive over geological timescales. Consider the challenges of preserving even natural fossils. While we have an incredible fossil record of dinosaurs and other ancient life, it represents only a tiny fraction of the organisms that ever lived. The vast majority of life forms simply decay without leaving a trace. For something as complex and potentially fragile as technological artifacts, the odds of preservation are astronomically low. Most technological materials are not designed to withstand geological pressures, extreme temperatures, or prolonged exposure to corrosive elements. Even if some incredibly durable artifact were to survive, it would likely be buried deep within rock formations, compressed, distorted, and potentially altered beyond recognition. Furthermore, the geological record itself is incomplete. Erosion constantly removes layers of rock, destroying the information they contain. Volcanic eruptions can bury vast areas, while subsequent erosion can expose older layers. The process is dynamic and chaotic, leaving us with a fragmented and often discontinuous record of Earth's past. We are essentially trying to reconstruct a complex narrative from a shattered book, where many pages are missing, and those that remain are often water-damaged and faded. The chance of a specific page detailing a prior civilization surviving such a process is incredibly remote. Even if a techno-signature were to be preserved, identifying it would be a monumental challenge. Geologists are trained to recognize natural formations, mineral deposits, and fossilized organic matter. They are not typically looking for evidence of ancient manufacturing processes or synthetic materials. The anomalies that might point to a prior civilization could easily be misinterpreted as unusual natural geological features, or simply dismissed as unexplainable oddities. It requires a shift in scientific paradigm, a willingness to consider entirely new categories of evidence, and a multidisciplinary approach that combines geological expertise with insights from materials science, chemistry, and even engineering. Moreover, the sheer scale of the Earth's surface and subsurface makes a comprehensive search incredibly difficult. We have explored only a tiny fraction of the planet's crust in detail. Vast areas remain largely unexamined, particularly the deep ocean floor or remote, inaccessible landmasses. Even if traces of a prior civilization exist, they could be buried beneath kilometers of rock, or hidden in locations that are practically impossible for us to access with current technology. The search for such evidence would require unprecedented levels of geological exploration and an entirely new generation of remote sensing and subsurface imaging techniques. The limits of archaeological and geological evidence are not insurmountable, but they highlight the extraordinary difficulty of the task. It's not simply a matter of looking harder, it's a matter of looking differently, with new tools, new theories, and a profound openness to the unexpected. The absence of evidence is not always evidence of absence, especially when dealing with timescales that dwarf human comprehension and geological processes that relentlessly erase the past. The search for a hidden civilization forces us to confront these limitations and to push the boundaries of what we consider possible to discover. Our understanding of what constitutes intelligence and technology is largely shaped by our own human experience. When we imagine a prior intelligent species, we often project human characteristics onto them: bipedalism, opposable thumbs, complex language, and a drive to build and manipulate their environment. However, the universe of possibilities for intelligence and technological development is likely far broader than our anthropocentric imagination allows. If we are to seriously consider the existence of a hidden pre-human intelligent species, we must expand our definitions and open our minds to truly alien forms of cognition and creation. Consider the diversity of life on Earth. Intelligence has evolved independently multiple times, albeit in different forms. Octopuses, for example, exhibit remarkable problem-solving abilities, tool use, and complex communication, despite their radically different body plan and nervous system compared to vertebrates. Their technology might involve manipulating their environment with their tentacles, camouflaging themselves with incredible precision, or even using water currents to achieve specific goals. If an octopus-like lineage had achieved technological intelligence millions of years ago, their civilization would likely be aquatic, their materials organic, and their impact on the geological record vastly different from our own. We might not recognize their tools as such, nor their cities as artificial structures. Furthermore, technology itself doesn't necessarily have to be based on metallurgy, combustion, or electricity, as ours largely is. A species might develop biotechnology to an extraordinary degree, engineering living organisms for every purpose, from construction to energy production. Their machines could be genetically modified creatures, their buildings could be grown biostructures, and their communication networks could be based on pheromones or bioluminescence. The traces they leave behind in the geological record might be unusual fossilized organisms, unique genetic sequences, or complex organic molecules that have no natural analogues. We would need to expand our understanding of what constitutes technology to encompass biological, chemical, and even geological engineering on a planetary scale. Moreover, intelligence doesn't necessarily imply a desire for expansion, resource exploitation, or even leaving a lasting physical imprint. A highly intelligent species might develop a philosophy of minimal impact, living in harmony with its environment and leaving behind very few traces. Their advancement might be measured not by the scale of their constructions, but by the subtlety of their interventions, by their ability to achieve complex goals with minimal disruption to the natural world. In such a scenario, detecting their presence would be incredibly challenging, requiring a search for the absence of expected natural patterns or the presence of incredibly subtle, almost imperceptible alterations to the environment. The very concept of civilization might also need to be re-evaluated. We tend to associate civilization with large centralized populations, monumental architecture and hierarchical social structures. But what if a prior intelligent species developed a decentralized, nomadic, or even entirely non-physical form of societal organization? Their culture might be transmitted through genetic memory, telepathy, or complex patterns of behavior that leave no archaeological record. The idea of intelligence itself is complex, encompassing everything from problem-solving to self-awareness to creativity. To assume that all intelligent species would follow a similar evolutionary and technological trajectory to our own is a significant limitation on our imagination. Therefore, the search for a hidden, pre-human intelligent species requires a profound intellectual humility. It demands that we not only look for evidence, but also question our very definitions of what we are looking for. It forces us to consider the possibility that intelligence and technology can manifest in forms so alien, so utterly different from our own, that we might not even recognize them as such. This broadening of perspective is not just crucial for the search for ancient Earth civilizations, but also for our ongoing quest to find intelligent life beyond our planet. By challenging our anthropocentric biases, we open ourselves up to a universe of possibilities where the echoes of other forms of intelligence, both ancient and alien, might be waiting to be heard. Earth's history is punctuated by a series of cataclysmic events, from asteroid impacts to supervolcanic eruptions, and from ice ages to rapid climate shifts. These events have profoundly shaped the planet's geology and the course of life's evolution. If a prior intelligent civilization existed, its fate and the fate of its techno-signatures would almost certainly have been intertwined with these planetary upheavals. Understanding these cataclysms is crucial to assessing the likelihood of a hidden civilization's existence and the potential for preserving its traces. Consider the Chicxulub impact event 66 million years ago, which led to the extinction of the non-avian dinosaurs. This was not merely a large asteroid hitting the Earth, it triggered a cascade of global disasters, widespread wildfires, a prolonged impact winter caused by dust and aerosols blocking sunlight, and massive ocean acidification. Such an event would have been devastating for any advanced civilization. Even if they possessed significant technology, surviving a global cataclysm of this magnitude would be an immense challenge. The physical destruction would have been immense, and the subsequent environmental collapse could have rendered the planet uninhabitable for their specific forms of life, or at least impossible for their technology to function. Supervolcanic eruptions like the Toba eruption approximately 74,000 years ago also represent existential threats. These events release enormous quantities of ash and gases into the atmosphere, leading to global cooling, acid rain, and widespread environmental devastation. A series of such eruptions, or an eruption of even greater magnitude, could create conditions hostile to advanced life and technology. The geological record of these eruptions, often preserved as distinctive ash layers, could potentially coincide with the disappearance of any potential techno-signatures, providing a grim explanation for a lost civilization. Furthermore, long-term climate shifts such as glacial-interglacial cycles can dramatically alter sea levels, reshape coastlines, and transform entire ecosystems. A civilization heavily reliant on coastal infrastructure, for example, could be completely submerged and destroyed by rising sea levels, or left high and dry by receding waters. The grinding action of glaciers during ice ages can scour entire landscapes, erasing any surface features and pulverizing artifacts. The dynamic nature of Earth's climate over millions of years means that even durable structures could be subjected to immense physical stress and eventually obliterated. The very processes of plate tectonics, while fundamental to Earth's long-term habitability, are also incredibly destructive to surface features. Continents constantly drift, collide, and separate. Ocean crust is continually created at mid-ocean ridges and subducted back into the mantle at trenches. A civilization's entire landmass could be slowly consumed by these processes, its cities and artifacts carried deep into the Earth's interior, melted and recycled into new rock. Over tens or hundreds of millions of years, Very little of the original surface of the Earth remains untouched by these immense geological forces. However, these cataclysmic events are not just destructive, they can also be agents of preservation. Rapid burial by volcanic ash or sediment can sometimes protect delicate structures from immediate erosion. Subduction zones, while ultimately destructive, can sometimes preserve fragments of ancient crust, carrying them deep before they are completely melted. The key is to understand how these processes interact with potential technosignatures. What kinds of materials might survive such events, and in what form? Could the unique chemical signatures of a civilization be locked away in metamorphic rocks, only to be revealed by careful analysis decades or centuries from now? The role of cataclysmic events highlights the extraordinary resilience required for any civilization to endure over geological timescales. It suggests that if a prior intelligent species did exist, they either succumbed to one of these natural disasters, or they developed technologies and strategies to mitigate their impact, perhaps even leaving behind subtle evidence of their struggle and adaptation. The search for a hidden civilization therefore becomes intertwined with the study of Earth's deep history, looking for anomalies not just in periods of calm, but also in the chaotic aftermath of planetary upheavals. These events are not just destroyers of evidence, but also potential storytellers, revealing the dramatic forces that shape our planet and the life upon it. The potential discovery of a hidden pre-human intelligent species on Earth raises profound ethical questions, both for the scientific community and for humanity as a whole. What would be our responsibility to such a discovery? How would we interpret their legacy? And what would it mean for our own sense of identity and purpose? Firstly, there is the question of interpretation. If we were to find compelling evidence of a prior civilization, how would we avoid projecting our own values, biases, and historical narratives onto them? We would be trying to understand a species that is not only alien in its biology and technology, but also separated from us by millions of years. Our understanding would be inherently limited, filtered through our own human lens. There would be a risk of romanticizing their existence, or conversely condemning them based on incomplete information. The ethical imperative would be to approach such a discovery with intellectual humility, striving for objectivity and acknowledging the vast gaps in our knowledge. Secondly, the discovery could have significant implications for our relationship with the planet. If a prior civilization existed and vanished, particularly due to self-inflicted environmental damage, it would serve as a powerful cautionary tale. This could galvanize global efforts towards sustainability, forcing us to confront our own unsustainable practices with a newfound urgency. However, it could also lead to despair or fatalism, the idea that all intelligent civilizations are ultimately doomed. The ethical challenge would be to use this knowledge to inspire positive action, rather than resignation. Thirdly, the impact on human identity and religious beliefs could be profound. Many cultures and religions place humanity in a unique position within creation. The discovery of a prior intelligent species on our own planet would challenge these anthropocentric narratives, forcing a re-evaluation of our place in the cosmic order. This could lead to a crisis of faith for some, while for others, it could inspire a deeper sense of wonder and a broader understanding of the divine. The ethical responsibility of those making such a discovery would be to communicate it with sensitivity and respect for diverse belief systems, fostering dialogue rather than confrontation. Furthermore, there is the question of potential contamination or interference. If we were to discover the remnants of a prior civilization, particularly if they were in a state of advanced preservation, what would be our ethical obligation regarding their remains? Would we excavate and study every artifact, or would we leave some undisturbed out of respect for their legacy? If their technology involved biological components, would there be a risk of introducing ancient pathogens or genetically engineered organisms into our current ecosystem? These are complex questions with no easy answers, requiring careful consideration and the development of new ethical frameworks. Finally, the very act of searching for a hidden civilization carries its own ethical dimensions. Should we invest vast resources in a search that might yield no results, or perhaps results that are profoundly unsettling? Is there a moral imperative to seek out such knowledge, even if it challenges our most fundamental beliefs? The pursuit of knowledge is often seen as an inherent good, but it is not without its potential consequences. The ethical debate surrounding the search for extraterrestrial intelligence, for example, often touches on the potential risks of making contact. The search for a hidden Earth civilization presents similar, albeit more localized, ethical dilemmas. Ultimately, the ethics of discovery surrounding a hidden pre-human intelligent species would require a global conversation, involving not just scientists but philosophers, ethicists, religious leaders, and the public. It would be a moment of profound introspection for humanity, forcing us to confront our past, present, and future in a way few other discoveries could. The responsible handling of such a revelation would be as important as the discovery itself, shaping how humanity integrates this extraordinary knowledge into its collective consciousness. The mere contemplation of these ethical questions already highlights the transformative power of this hypothetical discovery.